It came along and made Hello. Can you all hear me? Hi, everyone. I want to be able to hear myself and hear the audio. So I'm just gonna have one of my ears out. Hello, Father. I am not Hannah. Today is the BAJA science stream. So when Hannah and I were getting prepped for our wedding, I have my engagement ring and my wedding ring on, so proof of marriage. I made our wedding bands. So this is a little tangent, but come on, focus. It's not focusing, but oh, you can see it a little bit there. So these are resin rings. Hannah has one too. It's a tungsten band, and there are flecks of sandstone and different color opal and some amethyst, because my engagement ring is opal and Hannah's is amethyst, and they are just set with UV resin, so it's not as impressive as it sounds, because you just buy the tungsten band. I got it on Etsy, and then just bought, like, ground up opal and amethyst. Hello, my dear love. We have a guest appearance from a kettle. Thank you. Would you like something? No? My wife, everyone. I think you're familiar with her. Okay. Bye. Yep. Hannah's gonna be my science technician for the day. We need this for an experiment. So I'm gonna let it cool a little bit, because right now it's like boiling. It's at like 200 degrees and I need it around like 140. So I'm just gonna cool it until it's a little bit cooler. Anyway, so the wedding bands, you basically have a UV light, which Hannah had one, and then I also got one from my dad, Mr. Blast, in chat, because we were going up to the UP, and there's I will get to the bits messages. I'm sorry, everyone. I will get there, I promise. I'm not used to interrupting myself, and just like my ADHD brain, if I don't finish a thought, I won't finish it. So I'm gonna just finish this thought real quick, and then I will promise I will get to the bits messages. So we were going up to the UP, and there is a type of like stone called Uberlite that glows under UV light, and so Dad gave me a UV light, and we searched, but we couldn't find any because we weren't like on the right half of the state. So anyway, with the UV resin, you just solidify it with that light, and then like grind it down with sandpaper, and then you polish it, and it was really fun. So let's go to all of the bits messages and things. Okay, I scrolled too far down. So there we go. We have from Chiba Hawk 420. Sorry to sneeze. Sorry. From Shiba Hawk 420, they said they cheered 100 bits, so thank you. And she blinded me, and I'm assuming this is like she blinded me with science. I'm assuming it's a link to that song. Belmo Homestead with 100 bits, thank you, said, yay, science stream while I sew a pink tutu for kiddo pride float. That's awesome. I've been considering, so Hannah and I, we have a goddaughter, and she's 3.5 months old, and I've been considering making a tutu for her because I have some leftover fabrics and some leftover elastic like band stuff from the wedding, from things that I did. Let's see. Jamie the Bunny cheered 45 bits and said hi, Baja. Hello there, Jamie. Dregory term cheered 50 bits and said love the lipstick, thank you. This is NYX matte lipstick. It's Hannah's, I just stole it from her. That would be cute. Bob Watkins suggests that I make her a lab coat. That would be cute. I might do that when she's a little bit older. We definitely are gonna try and get her into like nerdy things, and it's my best friend's daughter. We've known each other since we were, I think, 8, so like 1st or 2nd grade, and we've known each other all the time, and we're very like similar in terms of things that we like. So Hannah and I want to get her into like Marvel and like comics and definitely science. Oh look, my wife, she's in chat. Hello, wife. I love you. Evil Dead Guy said you got a lot of flat earth questions when you read the Google form from us, right? I actually didn't. I think only one person, it was probably you, that asked about flat earth. And I am unfortunately not a physicist, even though I do have some physics goggles right here. Hard goggles to protect your eyes from any flying objects. These were from my year of physics classes that I took. And while I do know that the Earth is certainly an oblate spheroid, and there are very easy ways to show that gravity is real, I would like to cover some things that I'm more trained on for this stream. So I just realized that I went off on a tangent about our wedding rings and didn't finish my sentence from the beginning. So we're doing great today, everyone. So this stream, when Hannah and I were getting ready for our wedding, Hannah had a subathon. I don't remember how long that she went to raise money to pay for the wedding. And it went really well. And one of the tiers for if we got to a certain level of I think it was subs or something, but a certain level of support, there would be a BAJA science stream. And so that's what's going on today. And over the past month, I got some suggestions from people. And so anyone that filled out that Google form that I spammed in chat a couple of times, thank you. It was really helpful. Gnome Pickles with 50 bits says science. BAJA is gonna make it a gosh darn verb. Yes. And I want to point out that I have decorated the background. So I think my dad and brother got me this Halloween decoration last year, and it says trespassers will be used for science experiments, and I love it. And so I have some glass jars, which we will be using. I have a little microscope. It is a teeny tiny little Kent microscope. And it actually does work. It's hard to see, but there is a light that turns on when it's properly like touching the there's a little like metal part that's connected to the batteries on the bottom. But if you flip it over, you can also just use like ambient lighting, and it reflects it using the mirror. So this is an actual like functional little microscope. I have looked at like leaves under it, and it's pretty cool. So it does all the things. It raises up, has the lens and the objectives. That's what these things are called, objectives. And it's pretty cool. I like it. And then I have some books. So I have some vintage science books, and I also have a couple of books that I've gotten from like vendors or as awards over the years. I got a scholarship in undergrad for biology one semester, and they gave me a certificate and a book. And yeah. Hannah asked if I go outside to the outside freezer, do you want anything? there are like some shoestring fries in there. If you want to make those and bring them to me because I'm kind of hungry, that would be wonderful. But anyway, back to... Ooh, I'm sorry everyone, that was probably very loud. So I have some vintage books. I have a What's All This About Genetics, which is the small one right next to the microscope. That was a gift from my cousin. And then I have a vintage vertebrate embryology book, which is so cool. That was actually in lab, and it's going back to lab to sit on my desk when I go back tonight. And so this was given to me by Dad, Mr. Blast in chat. So this is really cool. Railcast with 24 months says 2 years and it's finally happening. I'm not sure what's finally happening. I think that the rest of the message didn't come through. But yay for 2 years. Thank you so much for supporting Hannah. We really appreciate everyone that not only supported the subathon, supports every single day, and also anyone that's here right now. I know I'm not Hannah. I'm not as Hannah, because that was very descriptive of my wife. This is how my wife is. She's like, but yeah. So we appreciate all of the support, including. I just heard a Hannah downstairs. So we Hannah's really behind on the stream. I love you. She shouted that what was that shimmy? That shimmy is my personality. I was just trying to, like, she's more personality than I am because she's used to this. This is her job. This isn't my job. I'm a scientist. And most of my job is sitting in lab and like sometimes shouting across the lab to my lab mates. And with that, Gregory Term with 50 bits says that's a big ass flask. It is a big ass flask. Look at that. I think that was also maybe a gift from... I think that might have been a gift from Mr. Blast as well. Or maybe it was Broha Blast, who I don't think is in chat, and that's kind of disappointing. I don't know what he's doing. But I also have another flask. I don't know where it is. I tried to find it this morning. But I found that one in my grandfather's basement when we moved into his house. So that is Mr. Blast's father, who I stole a flask from. So Mr. Blast says he's right here driving. Okay. Hello, Broha. Drive carefully. Ooh, there's a hype train. A hype train. Oh my gosh, there's a hype train. Okay. So Cold Stare, thank you so much for the sub and for the 31 months. Thank you so much for the 31 months. Kirthan, I'm actually like gonna cry. I don't know why. This is very like very cool. Kirthan with 1,000 bits says, may these bits propound more scientific discovery. Thank you so much. Bubba Homestead with 100 bits says science train, and then the Baja blasted emote. And ooh, oh! Oh my gosh! Oh my gosh! Oh my gosh! Gregory Term! Thank you so much! Oh, thank you so much for the 10 gifted subs! Oh, thank you! That's so kind! Evil Dead Guy asks, is that the same Flash from Breaking Bad when Walter tried to explain chemistry to Jesse? I think so. It's very similar, if not exactly the same. Oh my goodness. Oh, Overthought gifted a sub. Thank you so much for the sub, Overthought. Screaming at the Radio said, here are my last bits for science with 50 bits. Thank you so much. Also, I remember your username from the Google form. Thank you so much for filling out the Google form. Kirthan gifted 20 subs. Oh my gosh. Thank you so much. Thank you so much, Kirthan. 20 subs. Oh my goodness. Baja getting bit by the streaming bug. I don't know, maybe. I know Hannah's been trying to convince me to stream, but if I do, that would have to be something for after I finish up grad school. Right now my plan is to... Oh my god, we're 68% to level 7 of the hype train. Holy moly. That's incredible, everyone. That's so incredible. Thank you so much. Dave M1 with 200 bits. Thank you so much. But yeah, my plan right now is I'm gonna be finishing up fairly soon. Hopefully. Mr. Blast gifted a sub. Thank you so much, Father. We appreciate it. Thank you so much, everyone. I don't know how Hannah doesn't freak out every time she gets a hype train, like I don't know, it's very new to me, so it's also new to me to be like in charge of a stream. But yeah, like my plan right now is hopefully finishing up my PhD fairly soon. And then I want to just have a full-time teaching position. Right now, my desires aren't really like research. I think I'm kind of burnt out on research. I've been doing research for the last 6 years for my PhD, and I don't know. But I love teaching. I taught for a semester. I taught a junior level genetics course at my university, and I will get to the bits in just a second. We're at 97% of to level 7, which is insane. Thank you so much. And yeah, basically I just want to do full-time teaching, whether that's like at a community college or like, you know, the university that I'm getting my PhD at, or something else. But I'm really leaning towards teaching. I'm gonna pause the music. And we can just have this chromatin sitting on screen. Okay, let's get to the bits. Gnome Pickles with 50 bits says, outstanding, are you going to keep going after your masters? So I luckily live in the United States, so I don't have to get a master's before I start my PhD, so I didn't get my master's, and went right to my PhD. I know it's different in Europe, where you get a master's before you go get your PhD. My love says that she's preheating the oven for my fries, and I appreciate that. Gnome Pickles said, oh crud, didn't know you were going for PhD. My brain is forgetful. That's completely fine. I'm, I started my PhD fairly young. I was the second youngest person in my cohort. So it's not uncommon for people to still think that I'm a high schooler wandering around touring colleges. And not a 27-year-old PhD candidate. Azure Stone Dog gifted a sub. Thank you so much. And we're at 1% to level 8 hype train, which is wild. Thank you so much. The support means so much to me. And I appreciate everyone that's here for to talk about science. I really like talking about science, and teaching is something that I am really drawn to. Also mentoring. I've mentored numerous undergrads and younger grad students in both, undergrad and grad school. I also really love to do outreach. So I've done multiple outreach projects through my program at all levels. So going to elementary schools and doing experiments and talking to kids. I've also done more adult level outreach type stuff where I gave a talk about mRNA vaccines. So that wasn't strictly targeted towards children. Let's see. DJ Che with 100 bits says, damn kids these days getting their PhDs. I know. There's a lot of people getting PhDs because it's kind of like inflation. Everybody is going to undergrad now, and so to stand out in the job market, you need a higher than undergraduate degree. Yeah. I'm of the opinion that you don't have to go to college. I did it because if we're being honest, I continued into my PhD because I didn't know what the fuck to do with my life. But I knew I loved science, and I did research all through undergrad. And my first year of undergrad, I was actually pre-optometry. But that didn't last. I got approached by a group in undergrad that helped. My wife is laughing. I don't know what she's laughing at. But I was approached by a group that helped low income and minority students get to grad school, and asked if that was something I would be interested in. And I was like, yeah. So then I joined a lab, and they helped me get into grad school when the time came. Let's see. She must be really behind because I don't remember saying a funny thing anymore. Dave M1 with 200 bits. Thank you so much. Also, we got a level 7 hype train. Thank you so much, everyone. I cannot even explain how excited I am. Thank you so much. The Mirasama says you'd be a good, what's the term? Bill Nye is one. Science explainer. I think that the term is science communicator, at least now. My brother says hello, sister. Hello, brother. Alt Fact subscribed, and they have a 13-month streak. Thank you so much. And they say hi, Baja. Hello. Dave M1 with 1,000 bits. Thank you so much. I really appreciate it. Alt Fact asked if I want to be an epigeneticist, do I need college? Yes. Yes, you do. Siberian Winter with 245 bits says, funny how you stumble into your life's calling by not knowing what you want to do. Yeah. It was really interesting because, I was pre-optometry because I was like, okay, doctor. I didn't really know about grad school. So, like, I had no idea that grad school even existed. And when that program, like, reached out to me and was like, hey, grad school, I was like, okay, maybe I could do that. Like, I always loved genetics. I remember watching about the Human Genome Project when I was like 5. And I was fascinated. I loved it. It was so cool. And I loved doing science fair in elementary school. I grew up like a stone's throw away from Kettering University, which is a STEM school in Flint, Michigan. And yeah, so like I always loved science. And so I was like, okay, I'm just gonna go for it. Necrophage with 100 bits says, by any chance did you hear about the Republican bill to mark all food that has aborted fetuses in it? Yes, I did. Oh my gosh. It's absurd. It's so absurd because there isn't any. No food is made with aborted fetuses or developed with aborted fetuses. It's just insane. And the Republican was like, I think that people should be able to choose based on their religious beliefs or preferences what they eat. And it's like, everyone should have the preference that they're not eating aborted fetuses. That should just be a preference that everyone has, which is why there are no foods with aborted fetuses in them. I don't know if genuinely, I don't know. I don't know what's going on with people. It's absurd. Yeah. So, Shapamon, you're correct. We don't need the disclaimer right now. We will at some point. An Necrophage with 200 bits. Thank you. Um, Chefamon said, I tried to go into genetics in college for my bachelor's degree because I didn't know what I wanted to do. And I didn't do that great despite being interested. The timing of 2008 didn't help things. Yeah. Gnome Pickles with 50 bits. I chose to believe that there is just a betting pool between them who can say the silliest thing and get away with it. That is what is keeping me sane. Yeah, that's fair. That is fair. I hope that it's just something stupid like that. But I'm just kind of disappointed in the world sometimes. But so I think I'm gonna start. The hype train is over. Again, this is like my favorite little vintage science book. It's super cool. Mr. Blast actually like earmarked the mouse section because I work on mice, and that was very sweet. I took it to lab meeting, which in grad school you basically have lab meeting with your lab every week. And I took it to lab meeting and passed around, and my advisor thought that it was interesting, which I agree with. Yeah, everybody thought it was cool. J. William subbed. Thank you so much for the sub, and said, science stream, woot. Yes, it is a science stream. Woot. So look at this nice tie-dyed lab coat. I didn't want to steal an actual lab coat from our lab, just in case there are any contaminants, either there or here. But my lovely lab mate let me borrow her tie-dyed lab coat. So that was very nice of her. Okay, so to start, one of the questions that I asked on the Google Doc was whether you all would be interested in like understanding how I parse research papers, as well as talking about lab techniques that I use. And so everybody that filled that out, which was 9 people, said that they would be interested in those two things. So I kind of have some stuff planned for the stream, and it's going to be first talking about some lab techniques, and then I'm going to talk about epigenetics, which is really interesting, and I'm actually going to show some weird like videos about epigenetics. People are very strange about epigenetics. And then some another suggestion was to talk about some pioneers in the field that I study, which I thought was a really good idea. So I'm gonna talk about a research paper that is from someone that actually won the Nobel Prize for that research, and it's in the field that I study. So I thought that would be cool. And then another question was about like genetic sequencing and why it's become so fast over the past decade or two. And I thought that would be interesting, talking about genetic sequencing. So I'm going to try and get through all of that stuff. I do have to go back into lab later. I have to harvest some embryos. But yeah, I want to just start off talking about like what I do kind of day to day as a scientist. So my lab works with mice. That's our model organism. I've also worked with yeast, HeLa cells, and those are the 3 models that I worked on: HeLa cells, yeast, and mice. HeLa cells, I didn't end up joining that lab because I kind of have a moral objection to the use of HeLa cells. So they were wrongly obtained without permission from Henrietta Lacks, and it's disturbing. There's a book. It might be, I can't remember what it's called, but if you search Henrietta Lacks, you'll be able to find it. And it basically talks about, like, they were obtained from, they were like cervical cancer cells, and basically they are used because they propagate, like they just continuously grow in culture, which is what you need. You need cells that will survive when you're doing experiments, and those were the first ones that would survive that the culturing process, the tissue culture. But she didn't give permission to the people that took those cells from her and continued to grow them. And now, like, they're everywhere. Like, HeLa cells are a very popular model to use when you're studying DNA breakage and repair. Ivana B. Spink says, ethical or not, she is a hero. Yes, I completely agree with that. I think that I took a bioethics course in undergrad, and I loved that course. I loved it so much. It was wonderful. So the ethics of science is something that I think about a lot. Also, being a vegan, like, the using like animals as a scientific tool is also something that I think about. And my own personal thoughts are that I'm still minimizing harm because I haven't eaten animal products beyond like accidental like contamination for 6 or 7 years now. But I do kill mice for my job. I also, part of my ethical decisions are, I will still take medication that is tested on animals. And that's because, like, if I'm not alive because I don't have my meds, then I'm not, like, helping anyone. Hello, Halloween Town. It's nice to see you. But yeah, so ethics are interesting. It's something that I think about. And so I decided I didn't want to participate in using HeLa cells. And that's how I ended up in the lab that I'm in now. I said hello, Broha. Did you not hear me? I have this little mouse that a friend got me that usually sits on my desk at work. And I kind of wanted to talk about mouse handling, because that's also something that has a lot of like ethics behind it. And using animals in research, you don't get to just do whatever you want, right? So there are standards of practice, not only for the funding agencies and for the federal government, but there are standards of practice at your university or whatever, place that you're working at. So Chapamon says that's what people don't understand about veganism. They seem to think it's a zero-sum game rather than a choice because vegans have the ability to practice it. The image is not helped by certain vegans that also make it seem like it's a zero-sum game. Yeah, I don't know. I have my form of veganism, and that's just kind of what I do. I don't care what other people do. I used to be more strange about it, but not anymore. I know what I'm gonna do, I know what I do, and I know what I'm not gonna do. Like, there are some vegans that still eat honey. I don't eat honey. So it's a weird, like, everybody has their line, and you just kind of have to stick to whatever line you're at. So mice still have to be treated humanely and respectfully when you're using them for research. And that includes when you are doing the experiments. So for my experiments, we have to sack the mice, and sack means sacrifice. So you're killing the mouse. And I'm gonna switch cameras. So we have a little mouse here. So when you're handling mice, which is interesting, you pick them up by the base of their tail, and then when we need to genotype mice, we take ear punches. So it's like a piercing your ears, so they don't have blood vessels at the tip of their ears, and it doesn't hurt them. And so what you do is you pick them up, and then you put them on a grate, which is where their food is, and then you pinch at their necks, and they have extra fluff to scruff them, and then you tuck their tail between your fingers and you hold them like this, and then you just take the ear punch. So they're not getting hurt, they're restrained. Sometimes they can wiggle out because you're just holding them by their scruff, and they can bite you. So I had someone ask about how do you not get bit by the mice. Ivana B. Spanks says, okay, stupid non-scientific question. If you just need the embryo, can you not give them an abortion without killing the mouse? No, we can't. So I can explain that a little bit more, why we can't do that. So the reason that we can't just give them abortion and collect the tissue is we use pre-implantation embryos. So these are embryos that are either still in the oviduct, which is in mice, the squiggly little tube that goes between the ovary and the uterus. Mice have a bifurcated uterus, which means it's V-shaped. So they have two uterine horns, and then up here is the oviduct and then the ovary. And so to harvest those pre-implantation embryos, they are either in the oviduct up here or in the uterine horn, but not attached to it yet. And so to harvest those, we have to take out the uterus and the uterine and the oviduct and then flush them. I talk with my hands a lot, just so you know. And so that requires us to sacrifice the mice. And it's just like if anybody did like dissection in like high school or undergrad, it's exactly the same. You just dissect the mouse and take out just the uterus, and it's, you know, a quick and easy process. It takes a lot of getting used to. Number one, like sacrificing the mice takes a lot of getting used to, and doing the dissection. And a lot of people have a hard time with it. There are some people that they can't work with mice because, or they can't work with mice the way that we work with mice. And that's okay. Like, I had a friend, she rotated in the same lab that I did and ended up joining, but she couldn't. She cried every time she sacked a mouse, and it just wasn't for her. It wasn't something that she could sustain long term. First name bunch of numbers says, how many embryos do you usually get per mouse? That is such a good question. So it varies, and it can vary based on what type of mouse you're using, and whether or not they have had a litter of mice before, or if this is the first pregnancy that they're having. So we use what are called outbred mice. So those are the white albino red-eyed mice that you typically think of when you think of like a lab mouse. So those are outbred, meaning the opposite of inbred. So inbred mouse lines tend to be, the mice themselves are smaller, the mice are more combative, and they have a lot smaller litters. So the mice that we use, they're called CD1. That's just the name. They're outbred mice. They aren't, they're pretty big. Like, compared to, there are some mice called black 6 mice, because they have a black coat color. And so that's an inbred line, and they are really, really small compared to CD1 mice, and they can have like as few as 2 to 4 embryos per litter. And so that's why we don't use them, because we want the embryos specifically, and that just wouldn't work out. If you were having to sack a mouse to get 4 embryos every time, it would take so long. It would take so long to get the number of embryos that you need. So for our CD1s, you can get between like 11 and 20 embryos, and it varies. Jean Capra asks, can you show the different types on screen? Let me see if I can do that. That's a good suggestion. I'm gonna see if there's a comparison. And then I'll pull it up on screen. One second. I'm thinking of a very specific chart that I know. And I want to try and pull that up. Because it's a really good reference. Okay. Boo, why? I don't want to have to sign in. That's frustrating. The internet is being frustrating. Evil Dead Guy says, how long do you test before it is dead to deemed to be okay to test on people? We don't, so in my lab, we don't do drug discovery or develop drugs at all. So the first round of mice, the first round of clinical trials is testing on animals. And that takes, I think, like 4 or 5 years of testing, and you have to do like different stages of animals. I think you start with like mice, and then you would go to something that is a little bit closer to human, and then you move on to like the first stage of human trials, and basically like it can take decades for you to go from idea for drug to drug being used by people. Okay. So I'm gonna switch the screen. Nice. Okay. So I just searched lab mice on Google. But something that is interesting and I wanted to point out is this that I'm clicking on right here. These are what our mouse cages look like. So this is a really good like idea of what the mice stay in for our lab mice. And so they get food, water, and we have different types of enrichment for the mice. So there's like the nest bedding, there's cotton bedding, and then we also give them little huts, especially if they are alone. Because if mice are alone, they're social animals, and sometimes they do have to be housed alone. Sometimes they fight with each other and you have to separate them. And also, if a male mouse has been bred before, he can't be with any other male mice for the rest of his life, because they will fight. But mice are social animals, and so they need that enrichment, that stimulation, that, you know, to keep their brains happy. So we give them huts to play with. Sometimes like the rats that people use, I don't use rats, but there are rats housed in the same building as the mice, and they get like little toys because you know, rats are a lot how do I want to say that? Rats are a lot more cognizant than mice. So like rats remember they remember people. Mice don't. And so they get like better enrichment. They're also bigger, so you can keep less of them in like housed together. They don't have the same housing as our mice do because that would be way too small. So this kind of shows the okay, all right. So this kind of shows what different mice look like. So the black one behind here is usually like an inbred mouse. And that just refers to the fact that you take two siblings, mate them together, take two siblings, mate them together, and do that for like, I think 7 generations or more. And so you end up getting a very stable genome, meaning there isn't variation. So everything is homogenized, basically. So at each allele, which is like for your genome, we have 2 alleles. So each gene, there are 2 copies. And in an inbred mouse line, each gene is going to have the same 2 copies because they've been inbred so much that there isn't that variation. And with outbred mice, you don't have that. So our mice, which look exactly like this white mouse that has red eyes, they have whatever genome they have. One mouse will not have the same genome as its sibling. So basically they're good, and the white CD1 mice get fat. They get so fat. They to the point where like the vets, they're used to working with like our specific vets are used to working with other lab mice that are small. Ours can be healthy but huge. So it's interesting. I'm gonna look at some chats. Ivana B. Spanked asks, are your mouse embryos used in drug testing or something else? So something else. Our lab researches stem cells and tries to understand how stem cells develop. So the mouse embryo, and any embryo, begins as stem cells. So a stem cell is anything that can differentiate or self-renew. So that means it can stay the same, or it can become like a more specified cell type. And we basically study what factors help keep those cells, stem cells, and also what drives them towards specific cell types. So that's why we harvest embryos. And my stage of embryos that I work with is called between morula and blastocyst. So morula is a tight, compact ball of between 8 and 16 cells, and a blastocyst is between 32 and like 120 cells. That's just those stages are just when things start to change, just when some cells become different from other cells. And so I'm studying like what makes those differences happen. So Evil Dead Guy asks thoughts on the Calhoun mouse utopia experiments. If you could refresh my memory on what those are, I don't offhand know which experiments those are. A rat stream after I went to feed my friend's pet rat. Amusing timing. That is amusing timing. Okay, so let's talk about what I do after I have... One second. Hannah's coming. My love, she brought me fries. Thank you. Yes! The ketchup. And salt. Hannah says hello. Thank you so much, love.
No problem.
I have French fries, and they're nice, crispy shoestring French fries. Oh, these are so good. I was so hungry. The headphones have left. And also, don't tell Hannah, but the salt shaker is empty. Or the salt grinder. This isn't a shaker. Oh. No, thank you. All right, I fixed it. Okay, so Fennec Agami says, do you know the state of any push away from mice studies, because of how unreliable the results are? No, not really. Like, there are whispers of it, but mice are actually a really good model. And while some results can be unreliable in terms of how a specific drug could affect a human, because obviously mice and human are very different. You can still learn initial things from these experiments more quickly than something that is closer to a human biologically, like in terms of physiology. And sometimes that time to discover the first initial thing is more important than if it's exactly like a human. But we're all mammals, and human mouse embryo development is very similar. So for my field, at least, it's still a good comparison. There are some, big differences, but those happen mostly after the stage that I'm looking at. What else? What else did I want to say about these? So there are things that are unreliable about mouse research outside of the fact that they aren't similar to humans, as similar as a bonobo would be, or any other ape. And those are things like what type of mouse strain you're using. So a outbred mouse strain would be more similar to humans, just in terms of humans are outbred, and so that inbred versus outbred status could change how things look when you're doing experiments. Also, behavior studies and other things like that. Obviously, that's going to be a lot more different between humans and mice. But there are some really cool things that you can do with mice, like if you're doing immunobiology, so research on the immune system. You can have mice that have a humanized immune system. And so what that means is they're basically mice that are genetically modified to have a more human-like immune system. So you take the genes that are important to the human immune system development, and you put them into the mouse, and that mouse will now have a more human-like immune system. So there are ways to try and make things more reliable, more similar, but yeah, everything is going to be unreliable at some point, because humans are different from everything else that we test on. Evil Dead Guy says, this is the experiment I was talking about. It's what inspired the secret of NHIM movies and books. Okay, I'll click on this and see. We can talk about that maybe. And then Trevor of House Belmont with 100 bits. 100 cheers for awesome free biology seminar. Do we get course credit? That would be funny. That would be really fun though. Like if I could give some kind of credit for a stream, that would be fun. And thank you so much for the bits. So let's move on to what happens after I get these embryos, right? So you can do Nico Tenshihimi. I am so sorry. I'm really bad at pronouncing things in general, just like Hannah. With 7 months, thank you for the sub, said, I think I would like biology even more if BAJA was my teacher. Oh, that's so sweet. Thank you so much. I try and, express my excitement about biology and science in general. I think that's the most important, and also trying to understand where people are coming from, because you don't want to talk down to people, but you also don't want to talk above people. You want to talk to people at their level, at the level that they're at, because that's what's going to get you the most effective communication of science. So I'm not going to sit here and talk about, the trophectoderm and how it expresses CDX2, but CDX2 isn't expressed in the epiblast or the primitive endoderm. Like, that means nothing to most people. It means something to me and, maybe 50 other people. Bumble Homestead with 100 bits. I think BAJA University has to get their accreditation before they can issue credits. That's true. That's very true. Maybe I'll get an accreditation. Maybe. That'd be funny. Or I could just start my own university like some people do. Like someone I'm going to touch on today in the next segment of this stream. But anyway, I'm going to get back on topic and talk about what I do when I have the embryos. So once those embryos are out of the uterus, basically, I have them in a medium that, makes them happy. It gives them nutrients and stuff. And then immediately put them into a preservative. So, in this case, formaldehyde. And then I use some proteins to stain other proteins. Thank you for the hydrate. And so, basically there are, a bunch of different proteins found in these embryos. There is a couple that I look at specifically, and those are transcription factors. So transcription factors are proteins that actually bind to DNA and help to recruit the transcription machinery. So things that bind the DNA and then make RNA to then make protein. So transcription factors are basically like little red flags that sit on the genes that need to be transcribed, and then this protein that transcribes things sees, oh, this red flag, I'm going to bind here and then transcribe this gene. Then that gene, when it's transcribed, becomes mRNA, and it leaves the nucleus, goes out and binds to a ribosome, which basically just holds it. And the mRNA is read and translated into a protein. So just in general, I got a whiteboard. I can draw this on a whiteboard. But anyway, I'll keep talking while I think about some things. So basically, when you are translating a mRNA into a protein, there are what are called codons, and those are 3 amino acid segments that will then code for an amino acid. And I'm going to quickly draw this. I feel like I'm teaching my course again, because I TA'd during COVID, so everything was online, and so I wrote everything down and then showed it to a camera, so this is like bringing me back. Okay, so this kind of looks like a weird hamburger, but these are the 2 halves of the ribosome. So there's a small half, a big half. This is mRNA, and then this is tRNA, which has an amino acid stuck to it, and it has down here nucleotides that just so happen to be able to bind to these nucleotides, and this is a start codon. So basically it's like start here, and then more and more and more and more and more amino acids will bind onto that, and you will end up getting a chain of amino acids. So all's that to say, I am studying the transcription factors that are leading to, specific genes to be made into proteins for those cell types. And so different cells will have different things turned on at each time. So, for example, the cell type that I study the most, that it becomes like the supporting structures that surround an embryo as it grows. And that very specifically will express a transcription factor called GATA6. And if I want to look at where GATA6 is being expressed, I can use an antibody. And it's an antibody that is specific to GATA6. So let's say that this is GATA6. It would be like this, and it's shaped exactly the way that it needs to be shaped to just bind GATA6, and that's it. And then this antibody will have what's called a fluorophore. So it is a chemical tag that fluoresces when it is when it's exposed to certain wavelengths of light. So, one second, there are some bits. Azure Stone Dog with 201 bits. Gotta go watch VOD tomorrow, but I'm enjoying this. Thanks, Baha. Thank you so much for being here, and thank you for the bits. Okay, so, anyway, that's how I can visualize the protein that I'm working on and looking for. The way that I see that is because embryos are so small and because they're, just like 100 cells or less, you can do microscopy really easily on them. So we use confocal microscopy, which basically just takes, planes of images throughout the embryo, because embryos are optically clear. So they are effectively see-through. So instead of, for example, if you have a tissue sample from, let's say like a biopsy, so it's just a chunk of tissue, you can't image through that chunk of tissue because it's solid, it has pigment, it's not optically clear, you can't see through it. So they have to take physical sections of those tissues and then stain them and then visualize them on a microscope. With confocal microscopy, because embryos are optically clear, you basically just focus with the objective on a different plane each time and blast that embryo with the wavelength of light that will excite the antibody that you're using that's bound to your protein that you're looking for. And so then you'll see like places of light in the embryo where you're like, okay, yes, this is where like GATA6 is being expressed, or this is where whatever protein you want to look for is being expressed. And so after I image those embryos, you take them back and you want to harvest them from the slides that you're using so that you can do genetic testing. So basically, I just want to know, I work on different, sorry, I'm like blanking on a lot of words. So I work on different types of mice, some that are lacking specific proteins. And basically, I want to know, okay, if you lose this protein, what happens to this protein? Are there changes? Are there not? And to do that, I need to know what genotype it is, because I need to know, okay, is this embryo, is it just normal? Does this embryo have, is this a knockout? That's what it's called when you get rid of a gene. So is this a knockout? And to do that, I need to do DNA extraction, which I'm going to do an experiment now to show you DNA extraction. Avila 2022 says, takes me back to my biochem degree days, but 30 years updated. Yikes, now I feel old. That's funny that you mentioned that. I have a biochemistry book over here somewhere. I had the option of doing a biochemistry major in college. But I decided to just do straight biology, and then I was gonna double major in chemistry as well, but I was 3 credits, so 1 course away from having a double major, because I had to redo organic chemistry once. And yeah, so I didn't end up getting the double major, but I got a minor in chemistry. So 1 second, I'm going to grab some things. But first, Ace Laces says, Baja stream? Yes, Baja stream. And first time chat from Spoon Root 87. Hello. I wonder if I should go back to get a PhD, got a master's in biochem, but now I'm a teacher. I think it depends on what you want to do. If you want to continue being a teacher, then you probably don't need your PhD. But if you wanted to move on to something else, like getting back into industry or getting back into academia in terms of like research through university, then I would definitely say go back and get your PhD. I know lots of people that take big gaps of time to do something else and then go back to get their PhD. So there are a lot of people that are in like my program that are a lot older than I am, working on their PhDs, because they like got their masters and then went to go into industry, or was just like a lecturer somewhere and then came back to do their PhD. So yeah, it's depending on what you want to do, it can be super worth it, especially if you want to try and move into a different place. I'm currently thinking about a change in direction after coming out and home because of depression. If you're looking for a change of direction, I think that I would. I think I would go for it if I was you. Especially if you like have the funds. I don't know if you're in the US, but if you have the ability to get go back and get your PhD without like financial hardship, if you're looking for a change in direction, I think that it would be worth it. But I'm gonna do a DNA extraction, and so I'm going to... Oh, you're in Germany! Hell yeah. I would do it. If I was you, I would do it. So I'm gonna move my fries. I'm gonna grab a couple of things, and we're gonna do a DNA extraction. I don't know where to put my fries, because I also don't want the cats to come and eat my fries. My wife is laughing. I think I said something funny. All right. Chat. If you have long hair, and you want to do experiments, hair goes up. Always. Thank you. Thank you. Nico Shihimi, I'm so sorry. I wish I could pronounce that correctly. I know that I'm not. Says, oh, Baja, you look so cool. Thank you so much. And then these goggles are just for effect. Look how cool I look. These aren't even like goggles that I would wear in lab, because they're physics goggles. So they're to stop like chunks, like large things, from getting into your eyes. Like swinging little balls from getting into your eyes. They're not splash goggles, nothing like that. Okay, I think this is still warm enough to do the experiment. So some things that you need, and this is an experiment that we show like elementary schoolers when we do like science fairs for them. I love this experiment, and it's really simple to do. I wouldn't recommend doing it like unless you know what you're doing, if that makes sense. Like I can't say yes, go do this, you know. But it uses simple ingredients, simple reagents, and we're going to extract some DNA. So what you need, let me angle this up a little bit more. Oops, I'm sorry, everyone. Would my lovely assistant, my wife, please get me the isopropyl alcohol from the freezer downstairs? It's like in little conical tubes. She's getting it for me. Okay, I have a towel in case of spills, but hopefully we won't need that. I'm gonna move my phone. And for this, we have strawberries. So these were frozen strawberries, but fresh would work even better. But it doesn't really matter because you're going to be mashing them anyway. Which is why this is a good like experiment for kids. Because they get to like smush the strawberries. Hello, my wife. My wife has brought me ice cold isopropyl alcohol. These are called conical tubes, and they are properly labeled with the date and my initials, Baja Blast. You can go back downstairs if you want. Oh, you had a human fetus in a jar? That's kind of cool. We have mouse skeletal preps in jars in our lab, or we used to. I think my lab mate, I think she took them when she left. Okay, so you just want to mash up the strawberries really, really good. and then scientifically shake the bag. Okay. So you'll need a glass jar with warm but not boiling water. Okay. We are not cloning something, H-Baird. We are doing a DNA extraction. So if anybody has done a if anyone has done, I just dropped my phone and my whiteboard. I'm surprised that one of the questions people want to ask me that filled out the form, I'm surprised one of the questions wasn't, what's the most expensive mistake you've ever made in the lab? I ask everybody that, because everybody has a story. Yes, we are literally doing the strawberry thing, the strawberry DNA extraction. Okay. So, first, you mash up the fruit. And then we are going to add some water. Can't remember how much. How much water? Like 100 milliliters. So we're going to need 100 milliliters of water, which I'm going to eyeball. Okay. So we've got 100 milliliters of water, and then we need 2 grams of salt, which again I'm gonna eyeball. Okay, so we have water, salt, and now Dawn dish soap. And we need about, how many milliliters? We need like 4.5 milliliters. Yeah, that's probably good. Okay, so in this bag, we have made DNA extraction buffer. So if anyone has taken a COVID rapid test, you get a little tube that you put your swab into that says extraction buffer. So this is very similar, where it is a salty, soapy, watery solution. I love Nile Red. Nile's great. Okay. So basically what this extraction buffer does is it lyses open the cells of the strawberry and the nucleus, and into solution, so the liquidy stuff, will be all the DNA that came out of the cell. Okay, so I think that this is mixed up enough. And then we're gonna briefly put this in this warm water. I'm looking at some instructions online, but when we do this, in general, we usually don't put it in hot water. Like when we're doing it for like outreach for kids. Because usually we're at like a booth and there's a bunch of different science booths, and so like having kids sit and wait while you put it in hot water isn't, you know. But this is effectively what I do to embryos. Excuse me. I use an extraction buffer. In that case, it's actual like lab grade materials and not Dawn dish soap and table salt. Hello, Nicole. You're a good kitty cat. But yeah, so basically do DNA extraction. Okay, so now we have this slightly warm concoction of mashed up strawberries. It smells very strawberry in here. Okay. And we have a strainer. Hi, Lou. The cat heard me call another cat a good girl and is jealous. That's why she came up here. She says she's the only good girl. Yours truly, the one pony with 45 bits, says, Baja Blast. Hi, where's Hannah today? This is my science stream, which the Stanas earned during the subathon. And so Hannah gets the day off. I need to find something. I will stir with the handle of this brush that applied butter to Hannah's nipples once. Okay. Gonna pour the last little bit so that we have the optimal chance of getting DNA. Yes. Okay. It smells like soapy strawberries, which is exactly what you would like. Hey, love, could you turn that down? I can hear my own voice because Hannah's listening to me. Some people in chat haven't seen butter nips before. Oh, Okay. Yeah. So I don't just put butter on my wife's nipples. Her and Jake did a like charity thing on the Hannah and Jake channel before she came out, and before her nipples had drastically changed. And it was like, I think if they got to a certain level of donations from the community, Hannah put butter on her nipples and then licked it off. Yours truly, the One Pony. When will the Bible Reloaded and Bible Study return? If it's not going to continue on the Hannah and Jake channel, might as well start reading chick tracks on here. I don't know. That's up to Hannah and Jake. You know, I'm not going to say any more on that. Okay, so what we have now is some strawberry smashed stuff. And some not very clear liquid. So I might filter this through this cloth because I want it to be as filtered as possible. And I don't have like an actual filter. So we're going to filter this through this towel. I don't have any coffee filters. We don't drink coffee. But I think that this is working out pretty well. It's definitely clearing it up. There are so many like very adamant coffee people. I like tea. I just don't drink caffeine. Or at least not very often. Okay. All right. So we have more filtered stuff. And then you want to add ice cold alcohol very slowly. Because you want it to float on top of the strawberry water, strawberry extract. And so you can see it's sitting on top of the strawberry layer. Gray Fox 2343 says, Science Stream, let's go. I was hoping we would get one of these ever since you would come on and comment on different science related topics. Thank you for doing this. Well, thank you all, and thank you for subscribing. And this was a reward for the level of support that we got for the subathon. So thank you all. That's why I'm doing this. Okay. I'm going to bring the camera a little bit closer. Okay. Focus. Okay. So, at the interface between the smashed strawberries and the isopropyl alcohol, you can see these white streaks that are forming. Those are goopy little polymers of DNA. Okay. Yeah, so I need it to focus. There we go. That's a little bit better. Okay. Do I have something black that I can put behind this? 1 second, everyone. Okay. When I swish this around, you can see the strands of white stuff moving. So back there and also here. Those are goopy little globs of DNA. Yeah, this is a little bit better. You can see like all across the top. It's very cool. let's see if I can try and pull some of it out. Yeah. That snot looking stuff. That is polymers of DNA. Well, that was the DNA extraction. I'm glad that it worked. If only for just a tiny bit. With fresh strawberries, I used frozen, so with fresh strawberries I think you would get a little bit more DNA. Astrofox 9, is it possible to swab your mouth and extract your own DNA the same way, or does it require a more complicated process for that? The problem is, I don't think that with this method, I don't think that you would get enough cells from a cheek swab to be able to use like just household things to do a DNA extraction. Like, I think I used the equivalent of 4 strawberries. So if that gives you an idea of how many cells you need for this to work. But obviously with like lab grade materials, we can extract DNA like that from just a cheek swab or from like a blood draw. Because those are, you know, stronger reagents and, you know, a more thorough process. I extracted DNA from a strawberry, evil dead guy. Okay. I'm gonna take these goggles off. Okay. So now let's talk about what happens after you extract the DNA. So how do you know what genotype your mouse is if you're extracting the DNA? You just have globs of DNA. So you want to search for the gene that you're specifically looking for. And the way that you do that is with something called PCR. So polymerase chain reaction, that's what a PCR is. And I'm going to put on my super cute DNA helix jacket. So it's got like a bunch of DNA helixes on it. I love this thing. I've had it for a couple of years now. So PCR. What is PCR? It basically allows you to take that DNA extract, cut the DNA into fragments and amplify those fragments to see if you have the gene that you are looking for, or the variation of the gene that you're looking for. Can you use the DNA to make mutant monsters to take over the world, asking for a friend? Not strawberry DNA. But in all seriousness, I don't think that anyone has the skills to make a mutant monster that can take over the world. Gray Fox asks, are you looking to use your education in a teaching role or as a researcher? Right now, teaching. I am kind of burnt out on research. So that's, all I've been doing for the last 6 years. And before that, 3 in undergrad. I wouldn't be opposed to doing research at all. But once you leave research, it is harder to get back into. So I kind of am content and see myself just continuing to teach, whether that's at a primarily undergraduate institution, whether that's at a community college, whether I get a lecturer position at like an R01 school. It doesn't really matter to me, but when I TA'd, I knew that I loved teaching, and I know that I love mentorship. I know that I love science communication. So things like this, I think that's where I thrive. And while I am good at research and I do enjoy it, there are times when it is really hard. Really, really hard to do. And that gets tough because a lot of science is failure. And it gets tough on your self-esteem, and you get burnt out really easily doing research. And that's kind of where I'm at, where everything just feels really hard right now, So yeah, I'm gonna move away from research. Can I pet the mice, please? They look so very cute and soft. I don't know if they would like that, but I can tell you that they are soft, but they are bitey. They do bite. I have been bitten by mice. I've also had a mouse jump. So at the bench, you have their cage sitting on the bench, and then we have to wear disposable lab coats when we're in the mouse room working with mice. And I have had a mouse jump from the bench in its cage onto my arm. So that was an experience. That was kind of scary. Their teeth luckily aren't very sharp. They basically, if you so I showed earlier how we scruff a mouse. You pick them up by their tail, and you don't let them dangle like that, but you pick them up by their tail and put them on a stable place, and then you grab their scruff at the back of their neck, and then you fold their tail under your hand. And some people can actually do this with one hand. They can pick up the mouse here and do this without another hand. I cannot. I can't do that. My hands are too small. To me, it's probably the same level of skill that you need to crack an egg with one hand. And so, in theory, if you're scruffing them properly, they shouldn't be able to turn their head to bite you. Sometimes they can wiggle loose enough so that they can turn and like bite your hand. Luckily, we always wear gloves, and their teeth most of the time aren't like strong enough to bite through the glove. So they do try and bite you though. Let's talk about PCR, and I'm going to show you this song, this fun little PCR song that gets played in like every biology class. So this is made by a science company called BioRad, and they make thermal cyclers, which is the machine that you use to do PCR. So we can just watch this.
There was a time when to amplify DNA,
you had to grow tons and tons of tiny cells.
Oh, and along came a guy named Dr. Carey Morlins.
Said you can amplify in vitro just as well.
Just mix your tablet with a buffer and some primer. Nucleotides and polymerases too.
denaturing, annealing, and extending.
Well, it's amazing what heating and cooling and heating will do.
PCR, when you need to detect mutation. PCR, when you need to recombine. PCR, when you need to find out who the daddy is. PCR, when you need to solve a crime.
Unfortunately, there aren't closed captions for this. It says that they're unavailable. But basically, they're talking about PCR, and they're saying PCR for when you need to know who the daddy is, PCR when you need to solve a crime, like, etc. And the machine that he's holding is a thermal cycler.
To all the scientists out there doing PCR, BioRad salutes you with the all-new 1000 series thermal cycling platform.
This stream is not sponsored by BioRad. So let's use Google to our advantage and talk about some PCR. Okay, let's see if there's a way to make this. Okay, cool. So for PCR, it's basically the process of taking your DNA and you have to input the DNA, nucleotides, some primers, and also some proteins. So the primers basically are attached to the edge of the gene that you're looking for. And let's say if, for me in this case, I usually genotype for a a knockout gene. So I look for the intact version of the gene, and I look for a knockout version of the gene. And the knockout, basically, instead of having that gene, it has a chunk of random DNA inserted, so that that gene doesn't exist anymore. Yeah, H. Barrett says PCR is the slower COVID test that no one wants to wait for, but it's more accurate. It's also the thing that everybody says, oh, well, the creator of PCR says it couldn't be used for, illness detection. But that's not the case. Just because it wasn't made to do something doesn't mean it can't do something. And also, it's, yeah. But so the primers, you have different primers for each of the areas that you're looking for. And if like this one amplifies, then maybe it'll be the wild type version. And if this one amplifies, maybe it's the knockout version of the gene. And yeah, Gregory term says you can use a knife as a screwdriver. Yes. Yeah, like you can use a bunch of different things for things they weren't made for. I just used Dawn dish soap to help me extract DNA from strawberries. And so for the PCR, you basically have those primers and they sit on the DNA if that gene is present. And if they are sitting on the DNA, it will amplify and make a new strand of that DNA. And then once that cycle is done, the PCR machine heats up. So it's a thermal cycler. So you cycle through different temperatures, and when you are at 95 degrees, you are denaturing the DNA. So it means splitting apart those two strands of DNA. And then you can make new copies. And then you split those copies and make new copies. So each cycle you're doubling the amount of this gene that exists. And then after that, spoon root 87. Yes, that is correct. The next step after PCR is gel electrophoresis. And that's basically an agarose gel. Looks like gelatin. It's like a sheet of gelatin looking stuff. It has indentations at the top, and you load in your sample, and then you put it in a box that has a positive and negative end and some buffer in it, and you send an electric charge through the gel. And since DNA is negatively charged, it will go towards the positive side of the gel. So it'll run across the gel. And you will be able to see, okay, which gene is amplified. And each one, usually you'll make it so that the amplified section will be different sizes. What does PCR mean? PCR means polymerase chain reaction. So these are DNA strands, not toothbrushes. But yeah, so basically you can detect things with PCR. So it's really cool. And then you take the gel, and basically the samples that you load have a dye in them, and you just put the gel on a UV light, and you can see which how big that chunk of DNA that was amplified is. Yes, it's an agarose gel. And And yeah, so that's basically what PCR is. Are there any questions about like PCR or lab techniques or anything like that? I will be back in just a second. I dropped something. Ace Laces asks, what usually goes wrong? That's a good question. And Hannah also has a question. So give me 1 second. I'm going to wash my hands so I can eat my fries. Okay, so what usually goes wrong? There are so many things that can go wrong with PCR. To get one that is consistent, you have to troubleshoot. So it's not as simple as like ordering primers and then it'll just work. So you basically have to troubleshoot to figure out how to make it work. There are certain like variations of temperatures that make primers anneal better to the DNA, and sometimes you need more cycles or less cycles in the thermocycler to get the amount that you want. You can also drop your gel on the floor and then have to stick it back together to go and image it, which I've done. Everybody's done. If anybody's done multiple like gel imaging, you've dropped the gel on the floor or at least cracked it. They can also dry out. H-Bird asks, but wouldn't you have floor DNA if you drop it? The concentration of DNA that, number one, the concentration of DNA that you have in the wells would be so much higher than any DNA on the floor that it doesn't matter. The only thing that you need from the gel is to say, is this length of DNA here? Yes, then you're good. No, then what does that say? The floor DNA also isn't dyed, so putting it on the imager and imaging it, you wouldn't see that DNA anyway. You only see the DNA that's in the sample that you are loading. So it doesn't matter. Let's see. Hannah asks, as the strongest lab test, why does PCR not simply eat the other lab tests? I wouldn't say that PCR is the strongest lab test. It certainly has eaten other lab tests in terms of like popularity, right? I love my wife. Astrofox 9. Is this the process they use to make those stripy things on transparencies that they compare to see if DNA matches? Yes, yes. The stripy things, those are gel images. Let me use my handy dandy friend Google. Okay. So, basically, like, this is a gel box. So this is where the current is coming through, right? And then this is what a gel looks like while you're imaging it. And the actual image that the computer saves looks like this. So on the far right, you have a ladder, which is just standard sizes of DNA. And then you have your samples in the left 3 lanes. And you can tell that some are bigger and some are smaller. The smaller sized DNA is towards the bottom of the of the gel, because smaller DNA fragments are more easy to weave its way through the agarose, so they end up at the bottom of the gel. Larger fragments of DNA stay at the top because it's harder to weave long pieces through. Has PCR improved over the years? Yes. So when PCR was first thought of, you had to after each cycle, you had to go back in and add more polymerase, because once the polymerase reaches the temperature that it takes to denature DNA, it would degrade. And so that's not feasible. That takes so long to do, because each cycle you're re-adding more polymerase. And but they actually found in a species of, I think it was the vent worms, that live at the bottom of the ocean, they found a thermal stable type of polymerase, so you don't have to do that anymore. So the polymerase stays intact, and the same polymerase can be used through all the cycles. Sorry, I'm just reading through chat. See, Spoonroot's doing my job in chat. It's wonderful. I love having other people that know science in chat. What does the thickness of the band indicate? That is that is such a good question. So the thickness of the band doesn't say anything beyond this is the amount of DNA, and you can kind of compare between lanes, right? So you can be like, oh, this band is really strong, so there was a lot that was amplified of this. Humble Homestead with 100 bits. Oh dang, species are amazing. Maybe we should stop threatening their existence. Yeah. Any advice on how to explain this to non-biology familiar people? My biggest advice is to not get bogged down by the technical terms, not to like, of course, if people start asking questions, you can get more into how things specifically work, but just try and give like a overview of things in the plainest of terms that you can. Okay. So, I'm going to move on from that part of our science stream. We're going to close that. I don't really want the music on. Okay, so we're going to take a look at some of the weird stuff that people have to say about epigenetics. Evil Dead Guy says, does the dye you use help to see the cells? You won't affect the cells. Okay, so that's a good question. So if we're talking about like the when I'm looking for proteins and using like microscopy, the cells are already dead, so you don't really need to worry about whether or not the dye is affecting them. For the PCR, you are just dyeing the DNA. But in general, you do really need to be careful about to make sure that your tests, you're actually showing that something is occurring and it's not due to any kind of manipulation that you're doing to the cells. And so that's why we have controls. So we'll have, we'll do the same experiments on embryos that are just, you know, standard embryos as the ones that have like a knockout gene. So that we can do the exact same experiment and say, okay, these changes are strictly due to the loss of this gene. I have some things pulled up to look at. Hello, Astrostorm. What kind of embryos do you normally work with? I always work with mouse embryos, and they are pre-implantation embryos. So they are in mice between 2.5 days past copulation and 4 days past copulation. So those are called morula and blastocyst stage embryos, and they have between 16 and 100 cells. The Mirosama links a video and gives 45 bits of the kitty noticing me. Hello, Nicole. Oh, she's precious. I love her. 100 milliliters. So we're gonna need 100 milliliters
Yeah.
of water. Oh, baby. Which I'm gonna eyeball. Okay. Oh, so sweet. Thank you for sending that. Okay. So these people, there are lots of people that seem to think that with epigenetics, you can like master your environment and like be the master of your genes. It's really weird. It's very strange. So we are gonna listen to a little bit of this and then go to some other things, and I'll talk about epigenetics afterwards and probably during this.
Good morning. Okay. So I woke up a morning yesterday talking about my issues when I was growing up. Epigenetics. Epigenetics, I just recently discovered, is how your environment will affect you, affect your DNA, I believe. You know, I'm not exactly sure how DNA actually is active in my life. But I do have the experience of.
Does anyone mind if I like put this on 2 times or a little bit faster?
My body's physical.
Oh, yes. Astrofox says this is the biology equivalent of woo people using quantum mechanics jargon to justify their woo stuff. Yes, that is exactly. There are people that do talk about epigenetics the same way that they talk about the quantum mechanics.
Physical appearance changing due to the things that I eat, and I think possibly even the things that I do. So my body's physical appearance is definitely affected by my environment, the things I eat, the air I breathe, the rest I get, whether or not I'm connected to nature. I look a lot healthier and a lot different in the mountains. My chin is not so round. My face used to be real angular, but this is changed.
Yeah, that's not how epigenetics works. So she's attributing being in the mountains and having fresh air and stuff to a change in her face shape. So epigenetics can't change your bone structure, and these people take the idea that epigenetics is caused by your environment literally. They think that epigenetics can be changed with things that like short-term exposures to certain things in the environment. They also think your thoughts and your beliefs can change your epigenetics, and that has not been shown to be the case whatsoever. There are very specific things that can affect your epigenetics in terms your diet, like long-term sustained diet, development during childhood. Development is driven largely by epigenetics. So that's in terms of embryonic development and then slightly during childhood. So when cells are differentiating, they differentiate using a lot of epigenetics. So lung cells don't need the same genes turned on as liver cells. So epigenetics will mark these genes, say we're in a liver cell. This is a lung-specific gene. You don't need it. So it will mark it and it will not be transcribed. But your thoughts and feelings are not things that change your epigenetics.
Changed, and there's many different reasons for that. But it all boils down to epigenetics being affected by my environment. How is my mind affected by my environment? Well, these are physical. I was just, the physical is apparent, is visibly there. You can relate it to, you can do a test. I've done my own test to see, okay, if I eat this, how's it going to affect me? If I eat another thing, how's it affect me? Okay, so I've not kept a bunch of notes, but I do know that.
So, there is like a disconnect between the idea of epigenetics and this idea that your environment and your diet and things can affect you. So stress and things can affect you in terms of like mood and your brain and how you feel. But for there to be like these epigenetic changes, it's like a cell by cell process. And it's not making these like changes to your appearance. Like, you're not going to have a cell be like, oh, hey, like, I don't need this gene for some reason. Like, if you start taking a certain medication and it's, processing a gene for you, your body suddenly doesn't need as much of that protein or whatever. That cell could be like, oh, I don't need to produce this protein, so I'm going to turn that gene off. But that's not going to affect you phenotypically unless it's over like a really long time. So there was a case study, I believe, I don't have it pulled up, but of a young child that genotypically had the genes for dark hair color. However, because of some really terrible circumstances and their environment, they ended up having blonde hair. They weren't allowed outside, and they weren't exposed to like the sun and things like that. So as they grew up, they ended up having blonde hair because those genes that produce melanin for your skin tone and for your hair color and your eye color were epigenetically turned off because in that environment they weren't needed. That was a very extreme case, and that was a very that was just a one case study. So it's just that one person, and so that's not enough to prove that, like, hey, like, if you do something for X number of times, you can, like, change the phenotype of your hair, and you won't just suddenly wake up one day and have blonde hair. Like, one strand of hair might start being blonde up at the roots, but, like, that's not really how epigenetics works. It's not causing changes to your phenotype at random, like this woman who's an adult, she's fully developed. She's not going to just like wake up one day and have green eyes because she's in the mountains. Fenekagami says people really don't understand how hard genetic modification is for anything more complicated than a bacteria. Yeah. If you only eat orange things like carrots, your skin turns kind of orange. So that's due to a buildup of a certain protein. I think it's beta carotene, and it basically just builds up in the cells and it's orange. So it causes that pigmentation. It's not due to like epigenetics. Fenekagami says, don't some genes behave differently depending if it came from your dad or if it came from your mom? Yes. So there are a couple of different ways that genes from parents can affect you differently. So, number one, you could inherit like one type of this gene, so one allele from your mom, and then a different type from your dad, where like they have a different mutation or no mutation at all. So you might have, this is oversimplified, hair color is not caused by one gene, but let's say that there was a gene for blonde hair and a gene for brown hair. In this example, we'll just say that brown hair is dominant over blonde hair. This is not the case. That's not how things work. But just as an example, you would end up having brown hair because you have one copy of a brown hair gene. So that's an example of how like the same gene just mutated can be different because you get one from mom, one from dad. Also, there have been studies showing that certain genes, if they come from dad or mom, can have different epigenetic marks. And so if your gene from your dad, let's say your dad gives you the brown hair gene, but it has epigenetic marks that turn it off, and your mom gave you the blonde haired gene, but it doesn't have epigenetic marks to turn it off, you could end up with blonde hair even though you have the dominant brown hair gene. But those genes are very rare that behave differently based on like epigenetics from your parents, because when the embryo forms, this is kind of the issue with cloning. So, if you take a like nucleus from any random cell in your body, all of that DNA is going to be like epigenetically marked. The cool thing about reproduction is when the egg and the sperm combine, and their DNA combine, all of those marks go away. And that's not something that the body can do in other cases where it just mass wipes out like all of these epigenetic marks. And some of them do come back, and that's something that is called imprinting. So there are specific places in the genome where if there is a methyl mark, even if, you have this mass wiping out of epigenetic markers, some of them will come back. And that's something that's being studied a lot right now, because we don't exactly understand, like, okay, if we get rid of all of these marks, how do you know which ones to put back? You know? And that's really cool. That's like a next level of understanding what's going on when like zygotes form. So that's cool, and that's something we don't have an answer for right now. Like, you can hypothesize, but you don't know. And let's see. Let's go back.
I eat lettuce and drink water. I look different. It's not about weight loss. It's just about alkalinity.
Also, so number one, alkalinity. Alkaline water is just, there is no like regulation of alkaline water. You have no idea if it's actually an alkaline pH, and you shouldn't be like wanting to alkalize your body anyway. Your body very carefully like regulates its pH, and putting alkaline water isn't going to do anything. Your body's just going to be like, okay, why are you drinking this shitty alkaline water? Now I have to like rebalance my pH. Like, you're just making things so like, and yes, stomach has acid in it, so it's acidic. And then there are some people that add lemon to their alkaline water, and it's like, do you realize that you just made it not alkaline anymore, most likely? Because lemons are pretty acidic. Alkaline water is usually not that alkaline, if alkaline at all. So water is normally like a 7, and that's neutral. And then anything less is acidic, anything greater is alkaline. So like if you're having like a alkaline water that's like 8, it probably wouldn't even be 8. It might be like 7.5. And then you put a lemon juice, which I think is like a 3. It just doesn't make any sense. But anyway, this woman looks so much like my boss, it's kind of freaking me out a little bit.
And nutrition. So, epigenetics is a thing. Now I'm trying to figure out how this affects my mind. Because in my belief system, my mind is greater than my environment, because my mind perceives my environment. And my mind not only perceives it, but my mind directly interacts with it and influences my environment. Things that I'm looking at, as well as things within me. And this is what I am trying to accomplish, is a level of finesse, a level of development that brings me to a point where I am master over the effects, the outer effects of the world that everybody else is subject to, victim of, subject to, however you want to say that. Look how red my eyes are. My eyes are pretty red, and it's epigenetics. It's being affected by my environment. Did I get stoned? No, I don't do drugs. I should, but I don't. Oh. But my eyes are red. I think because, I'm going to call it an allergy. I have an allergic reaction to fudge cream Oreos. I need to quit eating Oreos. I'm sorry. Which means I need to quit buying Oreos.
So she thinks that epigenetics is causing her to have an allergic reaction to fudge cream Oreos because her body doesn't want them anymore because they're not healthy. At least that's what I'm picking up from what she's putting down. And that's not how things work at all. Like, I don't know if there have been any studies that talk about, like, foods causing epigenetic changes to immune system specific genes. Like, allergies happen after, so let's say this is my first time eating a French fry. I eat the French fry, and your body goes to work making antibodies to things. And maybe that antibody gets made wrong, and it says, oh, this is a bad thing. Like, you know, it shouldn't be causing this reaction to this fry. I eat another fry, I would have an allergic reaction because the immune system was first exposed to that French fry, and for some reason it is taking it as an allergen. It's taking it as a threat. Oh, Stark Raving 666 asks, what about those rare stories of people who develop allergy to meat later in life? There are one of the things that I know of that causes a meat allergy is getting bitten by the Lone Star tick, and it's because that tick has a specific protein that gets attacked by your immune system. It's trying to fight off the tick, and that protein is found in red meat. And so if you get bit by that tick, your body is being taught this thing is a bad thing. We're fighting this tick off, and then you're suddenly allergic to meat. So spoon root is correct. So the antibodies are edited randomly. So there is, for your antibody producing cells, they have a gene, it's VDJ. And so that gene can get like recombined or chunks lost, chunks replicated at random, and you end up with a mix of a bunch of different like antibodies. So whether or not something gets turned off or you develop an allergy depends on what type of B cell or T cell is like having the interaction. I'm stretching my knowledge here. I took a graduate level immunobiology course, but I'm not an expert. As far as I know, so there are memory cells in the immune system that are made, so that you can remember pathogens. That's a different response than an allergy. And the area of the body where those cells are made is different. Again, if I'm remembering correctly. And sorry, I'm trying to think of because it's so complicated, it's really hard to explain. But yeah, so the fighting off of pathogens is different than allergy response, and that's why you can get allergy shots to help you have less severe symptoms. So I used to get allergy shots because I'm allergic to cats. And that basically is trying to teach your immune system, okay, don't target this allergen with this type of immune response. Target it with this one. So you won't get the immune response where you have anaphylaxis or have really large histamine responses to those things. It is basically training your body to have a different reaction. Yes, peripheral immunity compared to central immunity. Thank you so much for being in chat, Spoonroot. This is wonderful. Let's see, there was something else. Oh yeah, so when B cells are made, they are supposed to be trained against yourself. So they get trained if they bind to self, antigens, which is an antigen is what is called it's called when a piece of something is presented to like an immune cell. So this is a really important filter. If it attacks self, it is supposed to be destroyed. It is supposed to be killed. That B cell is not supposed to proliferate. But with autoimmune conditions, those B cells slip through the cracks. So instead of getting caught, like, they get presented this antigen and it binds, and then it's like, oh, we gotta kill you. It escapes that filter, and then you end up with antibodies to things within you. So, like, my mom has ulcerative colitis, and that is an autoimmune condition. And the body attacks the colon. I think it's the top part of the colon, as opposed to Crohn's disease, which I think is the bottom part of the colon, or they're flipped. So yeah, so basically you end up getting antibodies, and like for testing for lupus, they test for anti-nuclear antibodies. So that's like the blood test that they give you to see if you have antibodies that are gonna attack itself, because lupus is an autoimmune condition. Okay, I'm gonna search for a couple of other videos. So Hannah taught me this neat little trick where if you want to get the weird videos, then you want to go to the most recent stuff. Like these ladies, they have the same views as the other woman that you can use epigenetics to like be the master of your world. That's how I found this woman. Okay, so this
Hey guys, in this video I'm going to
guy talks about this person, Bruce Lipton. So Bruce Lipton has a PhD in developmental biology, and this person talks about Bruce Lipton's work and 5 ways to use epigenetics for health and energy. So if it's not clear, neither of these people know what they're talking about. Bruce Lipton has a PhD, but he is, in my opinion, not a scientist. Like, just because he's done the science, it feels like he has gone so far off the rails that, like, he doesn't look at science objectively anymore. So let's get a little snippet of what this person has to say. And Bruce Lipton seems to be the man that started all of this in terms of thinking that epigenetics is like this spiritual thought-based, belief-based thing. So let's introduce him.
tell you Dr. Bruce Lipton's top 5 ways to stay healthy, which I know is a super important topic right now, and I really was interested in Dr. Lipton's opinion about this because he has such a unique and forward-thinking view on health in general. Now, if you don't know who Dr. Bruce Lipton is, he is a biologist, formerly a medical school professor, and he's one of the early pioneers in the science of epigenetics, which is all...
Okay, so first off, Bruce Lipton claims to be the person that discovered epigenetics, and it seems, this is my opinion, it seems that what happened is he kind of like incrementally over time blew things more and more out of proportion. So he starts talking about a study that he did, which I, number one, could not find, by the way. I looked at all of his publications, and I could not find the study that he was talking about. So I don't know if maybe it was his thesis work, and that thesis is not online, which I think he did his PhD in the 70s, and that is not uncommon to not have your thesis be online. Everybody that I know now, your thesis goes online, as well as a hard copy. But some people, you got a hard copy that you were given, and that's the copy. And maybe the school kept one, but sometimes they were lost in fires. So, that being said, it seems like he took, okay, I did this experiment as an undergrad. I mean, as a graduate student. I apologize. The biggest virus denier in Germany got a PhD with a thesis on marine viruses. Oh. Fun. So anyway, it seems like he was like, okay, I did this study in grad school. And then he, like, basically looking at different culturing conditions for, like, stem cells. And then it became, I did this study and it proved epigenetics. And then the story became, I was the creator of epigenetics. Like, it just grew over time. So he was not the first person to talk about epigenetics, and the definition has evolved since this, was Dr. Waddington. And the thing that I know him the most for is a idea in developmental biology called Waddington's landscape. Okay, so this is, do they have the original one? Okay, one second, let me see if I can find the original Waddington's landscape. Why is Google being this way? Okay. Yeah, there we go. Okay, so this is Waddington's landscape. And this is basically the idea that as cells develop, the ball starts up here. So all of these cells are the same. And as it falls, the ball can fall down a bunch of different pathways. But once it goes down one of the pathways, there are less and less offshoots it can take. So let's say it takes the left pathway. It can either continue going left, or it can go to the right a little bit and go to that cell type. And then his idea is once the ball gets down to its most differentiated state. Oh, Bubba Homestead, thank you so much for gifting SpoonRoot87 a sub. That's so nice. But once it gets down to its most differentiated state, it can't go back up and go to a different one. Because balls aren't gonna roll uphill. So, while that's not the case, and this was, I think, proposed from, it says here 1957. I was going to guess the 1940s, but I think the 1940s is when Waddington started talking about the idea of epigenetics to begin with. So if we go back over to this, Waddington's landscape has kind of been updated. So we have like normal development where you start at the top and then you fall into, you know, whatever cell type you're meant to become, right? Then there are these ideas of what if we could get a cell back to pluripotency. So pluripotency means the ability to become many different cell types. So it's one step down from totipotency. So technically, I think that this should say, like the top well where the ball sits and begins should be totipotency, meaning it can become any cell type found in whatever organism it belongs to. So for humans, placental cells, embryonic support cells like the yolk sac and the visceral endoderm, which are just the structures that help keep the embryo like intact, like in its amniotic sac. But it can also become germ cells. It can also become somatic cells. So all of the cells in the body, all of the support cells, that's what totipotency means. And then pluripotency is one step down from that. So the way that we think of it in my lab is pluripotent cells can become any of the cells in the body, including germ cells, but they are restricted from the pluripotent cells in the embryo. They're restricted from becoming the support cells or the placental cells. So they can't become all of the cells that the organism could possibly create, but they can become any of the body cells, any of the things that will go into the fetus itself. Then a step down from that is multipotent. So a multipotent stem cell is, like I said, a step down from pluripotent, where it can become multiple different cell types, like primitive endoderm, which is a tissue that I work with a lot. It's part of the embryo, and it will become the yolk sac and the visceral endoderm. So those cells are restricted to just becoming those support cells. It can't become any of the body cells. It can't become placental cells. So like basically the further down you get this ladder, the more restricted you become. And then you get to fully differentiated cells, like the cells you find in the heart of a fully formed organism, the cells that you, like skin cells. And you can't just hop between an eye cell being a skin cell. So this direct conversion that it's showing and you can't see because I'm blocking it. Basically, let's see if I can put this. Yeah. So above me, right here, is a depiction of what would be direct conversion. So directly converting a differentiated cell into another differentiated cell. So what my lab is trying to understand is basically, how do we have this normal development? Like this normal one over on the left How are we getting this traveling from this cell type to this cell type? And using that information, how can we do B? If we are going from here to here, how would we go in reverse? And then how can we get, if we go back up to a more potent state, can we go back down again to a different cell type? So that's basically what the lab I'm in is studying, using embryos. Because the embryos, they are 100% efficient at normal development. Mice know their jobs. And I'm acting as if they are purposefully doing this. Just a turn of phrase. So the embryo, to be able to go from a zygote to a fully grown organism, it has to be able to make stem cells 100%. Without stem cells, it won't live. So the embryo is the expert. It knows what it's doing, and it's going to teach us how to do it ourselves. And that's how I love to say that. I have an image in a lot of my PowerPoints, and it's like it's a mouse with a little graduate cap, and it says, how do stem cells work? Well, let's ask the experts. And the experts are the mice, the mouse embryos. So, basically, all that to say is epigenetics is very related to development. It is the mechanism by which we get this differentiation into cells. It's not the only mechanism, but it helps. It's also something that stands in the way of cloning. So one of the issues with cloning, let's take Dolly the sheep for an example. I'm not sure how many of you have heard of Dolly the sheep, but probably a lot if I had to guess. So Dolly the sheep was the first ever cloned mammal, and basically they didn't start off trying to clone. They started off researching something else, and they ended up taking the nucleus of this somatic cell, so a body cell. It was a skin sample from the original sheep, and they took just the nucleus from that cell and put it into an egg. So like a donor cell. And then they triggered it to multiply. And the reason why Dolly is so like miraculous is this didn't work for like most of the time. Like it is a very, very rare process, a very rare ability to be able to take this nucleus and have it actually develop into an organism, because taking this fully adult cell, fully differentiated cell, and using its nucleus with all of its epigenetic markers and all of its possible mutations, and using it as if it's a nucleus of a zygote causes problems. And that's why Dolly the sheep ended up dying so quickly. So you're taking a fully adult cell and forcing it to grow up and develop again. And through that process, you basically have essentially premature aging, because all of those epigenetic markers are still there. You're not having that process by which a fertilized egg goes through, where you wipe clean all of the epigenetic markers. and you're just having all of these, stay. And so she ended up dying, I think, of cancer, and that was partially due to the fact that the nucleus that was used and created all of these cells was prematurely aged. And yes, so they accumulate epigenetic markers. So like sperm and eggs, sperm less so because sperm aren't around for a very long time, but eggs really, really, really have issues with aging. And they can, even though they're supposed to be essentially in stasis, so they stay in the first cycle of forming until they are mature, they can still have these epigenetic marks forming. However, when they combine, there is the stage of reproduction in the zygote where there is a mass getting rid of epigenetic marks. However, if you get one of those stable marks that persists even after that, then you can have issues. So yes, they are more resilient to it, and even it's rare to get something that will stay a mark from mom into baby, that isn't supposed to stay. So, basically, let's continue with this video. I kind of want to basically use this as an introduction to Bruce. And I think that Bruce is really the person that kind of like started all of this. Like, even the woman before, it seems like even if she didn't get her ideas directly from Bruce, I think she got them from someone that got them from Bruce.
All about how the environment shapes the way that the genes express themselves, which is something that he expresses in his very popular book called The Biology of Belief. Now, I read his book recently, I've been watching a lot of his videos, and I wanted to make this video for you to condense it all down into 5 practical steps that you can take to keep yourself healthy. Now, you're probably listening to everybody else telling you to wash your hands 50 times a day and use hand sanitizer, never leave your house. And while there might be some truth to that, the theme of this video is going to be kind of the theme of Bruce Lipton's work in general, which is that the typical traditionally recognized causes of disease, which I like to summarize as genes and germs, are not the only considerations. I mean, a lot of people think that everything that determines their health comes from outside them. Either they were born with certain genetics, so therefore they're destined to get a certain disease, or they were exposed to certain germs, and those germs are going to cause them to get those diseases. But what I want to share with you is that regardless of the genes and regardless of the germ,
so having certain genes does predispose you to getting certain, well, I should say, having certain genetic mutations in these genes predisposes you to getting certain diseases. And there's nothing that you can do to stop that. Like, there are some genes that, let's say it's a recessive, a recessive diseased, so you would need 2 copies of the gene. One to have the disease and not just be a carrier. So you get a copy from mom, a copy from dad. Let's say it's a gene that is also necessary for life. That gene isn't going to get epigenetically turned off even if it's malfunctioning, right? because it's necessary for life, whether it is mutated slightly or not. So you're going to continue having that mutated gene being turned on. And after a while, you will get the disease eventually, because like these people seem to think that you can just think your way into being healthy. You can believe that you're healthy and cure yourself from cancer because the epigenetics of your body will change because of your beliefs. Harold Elman. I also love the wingnut differentiation theory. Nico 10 says, I feel like he's on the right track with some of his thoughts. I feel like a butt coming on. It's just this idea that like people think that epigenetics can do whatever you want it to do, and that you can harness control of epigenetics and turn on and off whatever genes you want to at random or at will. Thank you for joining us, SpoonRoot87. I hope that you have good sleep. I really appreciate you joining.
You have a lot of power to shape your own health, and in fact, the power that you have inside of you is much greater than the circumstances of your birth or the germs that are surrounding you at all times. Okay, now the first thing that we all need to do is just stop panicking. Fear shuts down the immune system, and there's a good reason for that. Fear, traditionally, is a response to something that's a clear and present danger. So, to use Dr. Lipton's analogy, if you're standing 5 feet away from a saber-toothed tiger, probably you're going to have a lot of fear because there's a clear and present danger in that saber-toothed tiger. Now, if you consider that there's a saber-toothed tiger beside you, and you also have a disease, you have germs inside your body, which of those two threats is the larger threat that you're going to want to get away from? Is it the germs or the saber-toothed tiger? Well, obviously the answer is the saber-toothed tiger. You're going to get out of there as fast as you possibly can, and that's why we have our fear response. And what the fear response does is it shuts down every part of our body that is non-essential for getting us the heck away from...
I don't know what these people's reaction to COVID was. I can assume that they probably thought, oh, like, I can just epigenetically control whether or not COVID enters my body. I genuinely don't know.
that threat or for fighting that threat, as the case may be. So the immune system requires a lot of energy to work properly. You know this if you've ever been sick and you feel really tired. Well, it's because your immune system is taking up all your energy. But if you were afraid, your body's fear response takes all of the energy away from your immune system and puts it into your arms and legs so you can run or you can fight. Now, normally that's a good thing because that keeps you out of danger. But if you're constantly in fear, then it turns into a really bad thing. If you're constantly watching the news and watching all these scary images and listening to them, trying to cause you to panic over and over and over again, because that's what the news does. That's the news's job. If you are in a constant state of fear, then you are going to be constantly shutting down your immune system and you're going to be unable to fight any kind of disease. So the first thing that you need to do is...
Okay. So, stress and fear does not shut down your immune system. Prolonged stress can affect your immune system. in terms of it can be slower to heal, like, and you can also, there are things showing that stress can make you get sick more easily. But it's not like shutting down your immune system. It's not like that. It might slightly dampen your immune system. Harold Edelman says this feels like an evangelical, but with the focus on genetics in place of Jesus. It is. Bruce Lipton he basically uses epigenetics as if it is proof for God. So it wouldn't surprise me.
Is you need to calm down. Stop panicking. Stop the fear. Stop the sources of the fear. Turn off the negativity. Turn off the news. Turn off Facebook if everything you see on Facebook is telling you to be afraid. Stop talking to people who are constantly pushing this fear on you, or at the very least, ask them to stop. Start meditating daily, or start watching funny movies. Whatever it is that you have to do to get your mind off of the fear, it will pay huge dividends for your health. And by the way, it might not be that you're afraid of the virus, right? There's a lot of other things that you could be afraid of right now. You could be afraid of the economic shutdown. You could be afraid of losing your job. You could be afraid of your business failing. You could be afraid of China taking over the world, right? There are a lot of threats that are...
The idea that fear over the threat of China taking over the world will cause epigenetic changes within you is just beyond wild to me. Like, I don't even know how to explain it. Like, they truly think that you can just think your way to health. They also think that, like, epigenetics is more important than genetics. And there are people that say Darwin was wrong because epigenetics. Like, they say that evolution isn't true because epigenetics, when that's not even close to the case. Epigenetics does not disprove Darwin's theory of evolution. Epigenetics purely means these are things that can happen on top of your genetics. So the genetics are still... Oh, I accidentally restarted the video. Genetics is the thing that... It's the base layer. But then on top of that, there can be other things that cause other things. It is complex. It is, like, almost infinitely complex. And these people just, I don't think, can understand that there can be more than one thing going on. Like, it's like as if you're trying to start your car and you have a bad engine. Even if you have a good starter motor, that's not going to help the fact that you have a bad engine. So if you have a gene that isn't working properly or has a mutation, having good functional epigenetic marks aren't going to do anything for you. But also, like, you could have a functional engine but a bad starter motor, and so your car still won't start. Like, you can have two things that are true and two separate things that are doing separate things, but work on top of each other. Okay, so let's look at, this is Quantum University. This is a school where you can earn a degree by Bruce Lipton. So, he wrote Biology of Belief, and let's just look at some things in his biography. Bruce H. Lipton, PhD, is an internationally recognized leader in bridging science and spirit, who is best known for the idea that genes are influenced by belief and DNA does not control biology. A stem cell biologist, best-selling author of The Biology of Belief, and recipient of some prize that I've never heard of. He's been a guest speaker on lots of shit. He got a PhD in developmental biology from University of Virginia. And apparently, in 1982, he began examining the principles of quantum physics and how they might be integrated into his understanding of the cell's information processing systems. His breakthrough studies on the cell membrane showed that the outer layer of the cell is an organic homologue of a computer chip, the cell's equivalent of a brain. His research at Stanford University School of Medicine revealed that the environment operating through the membrane controls the behavior and physiology of the cell, turning genes on and off. Yeah, so if anybody doesn't know, having a PhD in biology does not make you qualified to study quantum physics. Also, I looked at his papers. I looked at everything that he's published. And none of it says this. While the cell membrane is the outside of the cell, and it has a lot of signaling proteins embedded into it so that cells can communicate with one another, so that hormones can signal to cells, so that minerals like salt and other things can pass through the lipid membrane of the cells. That is not the same thing as it being like a computer. The cell is not thinking about things. The cell is, there is a protein and there is a physical change happening when it binds to its signal. And then that change in the protein will be a conformation change through to the end of the protein that's inside the cell. And then that conformation change will change something else, which changes something else, which changes something else. It's a cascade of different physical changes or chemical changes to different steps that can then ultimately change what genes are being expressed, what cells they're being expressed in, and it can change like epigenetic marks. Fenekagami says, correct me if I'm wrong, but isn't, oh, also with 50 bits. Thank you so much for the bits. But isn't Darwin to evolution what Freud is to psychology? He was a cool guy that got things started, but basically a quack by modern standards isn't really relevant at all to the discussion. I don't think that Darwin is quite as irrelevant as Freud is. Darwin did get a lot of things wrong. He did have some really bad views for he was racist and he was sexist and he wasn't a great guy. But I will say that something that he did do well were his like scientific observations. And yeah, Miscellaneous says, I think Darwin was more right about his thing than Freud was. And I think I would agree with that. He based things on direct observation. And while if you looked at his stuff today, it wouldn't tell the whole story about what is actually happening. It was a good starting spot, like you said. Okay. I'm going to click on this YouTube video and see how long it is. Oh, it's 4 minutes, chat. Harold Elberman says, a cell biologist expert in quantum mechanics is like a rocket scientist declaring him a master bricklayer. Yeah. Yeah. So you can see in the recommended stuff when Bruce Lipton is searched, things like law of attraction coaching pops up. Like, these things are being used as if you can manifest things using epigenetics because your thoughts change the way that your genes are expressed.
In Biology of Belief, Dr. Bruce Lipton, PhD, outlines a new understanding of life based on his pioneering research with stem cells at Stanford University. In his book, Dr. Lipton proclaims that genes do not control biology and that cellular perceptions of the environment are the primary factor in biological processes. Proteins are the stuff of life, the physical gears that orchestrate the movements of biology. There are estimated to be about 100,000 different kinds of proteins in the human body. Today, medical students and practitioners are still operating under the assumption that genes, the blueprints that proteins are made from, are the primary factor in biological processes. When James Watson and Francis Crick first visualized the molecular structure of DNA in 1953,
Fuck Watson and fuck Crick. And that's my professional opinion. They did not first visualize DNA. They didn't. That was an X-ray crystallographer named Rosalind Franklin. And then they stole her work. And she died like a few years before Watson and Crick earned their Nobel Prize for the structure of DNA. So and Nobel Prizes aren't posthumously awarded, so she didn't get recognition for that. Angel of the Grove with 45 bits. Didn't come here today expecting Baja Science Stream, but I am here for it. Well, thank you for joining us. Yeah, so that makes me angry. Also, I don't remember which one it is, but one of these people, Watson or Crick, is just a raging racist. Yeah, so that's my rant about Watson and Crick.
The scientific community believed they had found the ultimate secret to life. The widely accepted understanding is that genetic information stored within the DNA is enough to explain all of molecular biology and heredity, and is the reason why living organisms look and behave how they do, in sickness and in health. The old scientific paradigm espoused that inert genes were the brain of the cell, directing and controlling which proteins become expressed in every cell, and that we are essentially all just victims of heredity. After doing experiments with enucleation, a process where the genes are removed from the cell, Dr. Lipton and other experimenters found that cells lived normal lives for up to 2 months or even longer before their proteins wore out and they died.
I don't even know what to say. Just because a cell can survive in a dish, and they're not even like, number one, what kind of cells were they using? Number two, they were in a dish. They're just plopping along. That doesn't mean that they're functioning properly. It's not just about the cell being alive and proteins still existing. And that would be like saying, we removed the kitchen from this house and wouldn't let the inhabitants get out of the house. But they were still alive a month later. Even though they don't have a kitchen. They couldn't have possibly eaten. They don't have a kitchen. But they still have food that was already prepared before the kitchen left. Right? Like, it's the equivalent. You still have, like, without the DNA, you still have proteins, but you can't make new proteins. Once those proteins degrade, they're gone forever if you don't have DNA. They're not living normal, happy lives. It's a dish. They are not in the organism. Like, I mean, okay. So, Astral Storm, RNA degrades much more quickly than proteins. So, RNA, if we get to the point where proteins are degrading, the RNA's gone already. And sorry. So like, just because they're alive doesn't mean that they are functioning. It doesn't mean that they are doing the things that they need to do. It doesn't mean that they're signaling properly. You can have a like a muscle cell alive in a dish. That doesn't mean it's acting like a muscle cell. It doesn't mean that it's contracting like a muscle cell. That doesn't mean it's signaling like a muscle cell. It just means that you have a cell sitting in a pool of liquid. That's a good point. Astral Storm says, what did they pick as the endpoint? Lysis? And to that, I don't know. I would assume so. But to, like, also, I would love to see this experiment. Because number one, I don't really believe that it exists. Number two, if it exists, and the way that it's being portrayed here, if it exists, what methods were used? Because if they're taking a dish of cells that have been enucleated, so no DNA, and they're just letting them like sit there, right? And then waiting until some amount of time, this says 2 months, and then taking all of that liquid and grinding up all the cells and being like, yep, proteins still exist in here, so they're fine. That wouldn't be a good experiment. Because, like, there were amino acids found on an asteroid that fell to Earth that were older than the Earth itself. Just because there were amino acids present doesn't mean that there were proteins. It doesn't mean that there were living things. The same way, just because there are proteins, it doesn't mean that the cell was alive.
An observation that contradicts the primacy of genes in cell biology. The genetic information stored in DNA is the blueprint from which all of the body's proteins can be made. Modern science has mistaken the blueprint, the DNA, for the contractor who actually builds the house. So, if the genes are not the brain of the cell, what is? Introducing the cell membrane. At just 7 nanometers wide, this phospholipid bilayer is covered in hundreds of thousands of different receptor proteins. These receptor proteins are each specialized to interpret different signals from the environment and then relay that information back into the cell. When a chemical messenger like a hormone or a neurotransmitter binds to a receptor protein, like a key going into a lock, the receptor protein activates corresponding effector proteins inside of the cell, initiating a cascade of chemical reactions within the cell. These are called IMPs, or integral membrane proteins. This receptor-effector protein relationship in the cell membrane is how a cell perceives and reacts to its environment.
Okay, the issue is that they're acting like the cell membrane is actually actively doing these things. Like it's alive in the sense that it's thinking and feeling. Angel of the Grove with 45 bits says, I think membrane just sent my brain cells into lysis. It's just so frustrating because I don't think that anyone has ever proposed that DNA was the end-all be-all. So to begin with, before DNA was found to be the heritable material in the cell, people had proposed, oh, maybe proteins are the heritable material. Maybe RNA is the heritable material. But then it was shown to be DNA. That doesn't mean that the DNA itself, the nucleic acids, are the only things that matter. But in this case, Astrostorm says a cell membrane does a bunch of important things, and it has a lot of advanced proteins on it too, but it requires ribosomes, membranes at the very least, and operational ribosomes. That means which stable mRNA or DNA that is made into it. Yes. It's they're taking it. Sorry, this is really hard for me to talk about because it's so frustrating on a level that is hard to explain. Because like some of the things that they're saying are correct. Like, yes, there are membrane bound proteins. The cell membrane is a lipid phospholayer, and signaling occurs using these proteins, right? But they're like warping it, and it is hard to explain that warp. I agree. This is why we need better education in science, because think about this. This is something that is being taught because Bruce Lipton said it. This is essentially like Bruce Lipton went to Fiverr and said, hey, read this thing for me. He has a PhD. But somewhere along the line, he kind of lost the plot. So, like, he has the knowledge. It's just become something else. And he ultimately thinks that belief in God changes your epigenetics. And I've seen people say that if you believe that you don't have cancer, your cancer will go away because of epigenetics. And again, Astrostorm is correct. Something with just a membrane and genetic material is called a virus. Yes, so viruses are just genetic material. There can be RNA or DNA viruses. And they are encapsulated in a protein layer. Whether it's shaped like a bacteriophage or whether it's shaped like the coronavirus. It is essentially genetic material and wrapped in a protein layer. So that's what they're trying to portray. They're trying to portray that epigenetics is just magical thinking. But in reality, it's not. Epigenetics is the let's see. Okay, let's see what you guys can see. Let me make this bigger. Does that work? No. That didn't work. How can I? Okay. Let's remove this and then okay. So I need to try and like make this smaller. Sorry, everyone. I really want this image to, like, cooperate with me. Oh. Maybe I got it? Okay, that's definitely better. Okay. Terrific. Terry716. Hi, Baja. Great to finally see you. Heard nothing but good things about you. Oh, thank you. It's good to see you too. So let's talk about epigenetics and what it actually is. So it's not this like, it's not what they're portraying it to be. It's not this big, ultimate, most important thing. It is just a mechanism by which things affect what genes are being expressed in what cells at what time. So the things that have been shown by studies, by scientific studies, to affect epigenetic marks is development. So the process of going from totipotency to a differentiated cell uses epigenetic markers. Environmental chemicals, so like long-term exposure to certain things in the environment. Drug pharmaceuticals, so taking certain medications can cause certain things to be turned on and off. For example, if you are taking something like maybe an SSRI, and this isn't exactly how it works, but just an example, if you are taking an SSRI, it's a selective serotonin reuptake inhibitor. So that means that your body isn't going to get rid of the serotonin as quickly as it normally would. So if you have a bunch of serotonin sitting around, then you don't need to make more. So maybe in this neuron where there's a bunch of serotonin, it has an epigenetic mark to turn the gene for making serotonin off, because you don't need as much serotonin. Aging, so the more you age, the more epigenetic marks you can acquire through different things. And diet. So if we look at the chromosome, this is, when everything's all packaged up and your cell's getting ready to replicate. The chromosome is all tightly wound up, all the DNA is nicely packaged, and you get that like cluster in the center of the nucleus where everything's lined up nice and pretty in these X-shaped chromosomes. That's not how it normally looks in the nucleus. You get like different areas of different compactness. So if something is being actively transcribed, so if it's actively needed by the cell, then it is more open. If something isn't needed by the cell, then it will be like bound up by one of these histones. So in the figure, you can see the blue, teal kind of colored balls. Those are called histones. And those are the things that the DNA gets wrapped around so that things can be packaged all nice. A histone can act as an epigenetic thing on two levels. So histones have tails. There can be histone methylation, which is a more active version of like an epigenetic mark. So actively, the histone tail can get methylated or acetylated, and that will, keep that histone ball closed, so the DNA won't unravel off that histone. Also, there is a more passive way that histones are regulating genes, in terms of if there is a histone here, you can't get transcription because there's a histone there blocking it. So there's not an epigenetic mark there necessarily, but the histone itself is acting as a blocker to transcription. So if that histone is blocking a gene, you won't get transcription of that gene. There can also be DNA methylation. So directly on the DNA backbone, so the DNA is a bunch of nucleic acids. Their backbone is phosphate groups. And so those can be methylated, and that can activate or repress a gene. Usually it's thought of as repressing. And so that's like a second level of epigenetic mechanism. It is instructions for what the cell needs in that moment, basically. It's like these conditions are triggering these epigenetic marks, so we need these things and not these things. Tim J5777 said, hey, did you steal Hannah's channel? For today, it's the BAJA Science stream. So let me think about what I want to talk about next. The Marasama says, hey Baja, I gotta head out, but this was fun. Thank you so much for coming, and give your kitty a scritch for me, please. Okay. Let's finish this video.
A molecule in the environment binds to a receptor protein. An effector protein gets activated, and the chemical release inside the cell makes its way back to our cell's nucleus, where the DNA is opened up, so a new protein can be made in the process of transcription. All the functions of DNA depend on interactions with proteins. For example, within the chromosomes, proteins such as histones compact and organize DNA. These compact structures guide the interactions between DNA and other proteins, helping control which parts of the DNA are transcribed. For a gene to be expressed, a sigma factor protein needs to bind to RNA polymerase for it to split the DNA and be able to access.
P-Meal with 300 bits says, Baja Science Stream, yay. Thank you. Thank you so much for the bits. Astral Storm says, this is trying to push protein supremacy. Literally. It literally is. It's just so... It's so weird. It's acting like proteins are very important, but DNA is also very important. It's like, if you don't have instructions to build a section of a bridge, you're not going to be able to have the bridge. Like, whether you have epigenetics or not, whether you have someone being a director, if epigenetic marks were directions, nothing's going to happen if you don't have the blueprint. Right? It's just frustrating.
access the blueprint. Different sigma factors
Oh,
are
no.
utilized
I
under
hear my
different
wife.
environmental conditions. These specialized sigma factors bind the promoters of genes appropriate to the environmental conditions, increasing the transcription of those genes. The genes chosen to be activated and synthesized into new proteins are the direct result of signals from the environment interacting with receptor proteins in the cell membrane. This is the molecular basis for the environment
Love
being
you.
the primary factor in biological processes. Understanding this complex interaction between environmental conditions and gene expression leads to a marvelous new understanding of biological development, where evolution is no longer a mindless game of chance based on random hereditary variants, but an interactive dance.
See, this is where it gets really weird for me, because they're like, oh, evolution is no longer a game of chance. Like, it's an active thing. No. There is no direction of evolution. Evolution purely is this entity fit for this environment? It's not a directional thing. If the environment, like tomorrow, started selecting for people, or started selecting for things that can live more in the cold, then it will. If it starts selecting for things that survive better in the warm, it will. The selective pressure, it's based on the environment. The mutations that exist are random. If a mutation makes you better fit for that environment, it'll stick. But if that same mutation happened in a different environment, maybe it wouldn't make you more fit. Maybe it would make you worse fit. And yes, Astrostorm. Evolution also is extremely slow. Epigenetics is fast. Yes. Epigenetics affects the individual. One organism. Evolution is population, generation upon generation upon generation of change. But I think it ultimately comes down to, they think that God and your belief in God is driving your epigenetics, which is controlling your genes. And it's so weird.
Between organism and environment. Find out more at quantumuniversity.com and enroll in Dr. Lipton's Biology of Belief course.
Okay. So, I'm gonna have to go soon. I want to leave you with the knowledge that Bruce Lipton has a YouTube channel. And let me find. Okay.
55.
So this is gonna be very frustrating. But it is what it is. So this is Dr. Lipton. This is Bruce. He has a PhD in developmental biology, which is a field that I have very intimate knowledge of. actively work on stem cell research using mouse embryos as a model. So, let's listen to him.
5 years ago, I ended up at the graduate school at the University of Virginia in the biology department. And I was working for one of the most interesting and profound scientists of the day, Erwin Koenigsberg. He was one of the fathers of the cloning technique of stem cells. So while 55 years ago, hardly anybody in the world even knew what a stem cell was, I had the greatest opportunity of not just knowing stem cells, but actually growing them and cloning them in tissue culture. When we talk about stem cells, there's several different varieties of stem cell. A basic stem cell is called a totipotent stem cell. That means total potential to grow any kind of cell in the human body, be it skin, muscle, bone, brain.
And I think that this video highlights a really important issue. When he is talking about the things that he is actually educated on, he gets almost everything right. But he then tries to take that, I know all of this about this very specific thing, and say, oh, I can research quantum physics and the cell membrane is the brain of the cell.
These are basic stem cells that can replace anything. But the research I was working on was on a more restricted developmental stem cell, and it's called a myoblast. This is a cell that you can identify early in the embryo that will become the precursor of the muscle in the body of that embryo. So my research was to take out myoblasts and clone them and grow them in culture. And you say, but why? And the answer is very profoundly important, because basically we needed to have an insight in how does muscle form? What are the mechanics that control the development of muscle?
See, like, all of this is good. All of this is fine. This is exactly how I explain my research, basically. I work on a less restricted stem cell. So he works on myoblasts, which basically only become muscle, but I think it can become different types of muscle cells. I'm not really familiar that well with myoblasts, but the cells that I work on are multipotent. They can become more than this. KBS 666 says, I have a PhD in mathematics. I can sort of muscle through a quantum mechanics article, but I don't really understand it. I doubt a biologist would. Sorry, Baja. Yeah, I know. I completely know. Tunamon says, I like stem cell research. It's closely connected to lab-grown meat, which is really fascinating. Oh, I completely agree. I think that lab-grown meat is really interesting. I, as a vegan, would never eat it, and that's my personal view on it. I don't see myself eating meat ever again. I like meat substitutes, but lab-grown meat just isn't something that I think I could stomach. But that's different than other vegans. There are some other vegans that would be completely fine eating lab-grown meat.
More specifically, actually, it was the funding that I was getting from the Muscular Dystrophy Association to do this research for a very important reason. In muscular dystrophy, there's a breakdown of the muscle, and there's a problem with the regeneration of that muscle. So by working with the stem cells that generate muscle, we were going to get some insight into the mechanics of how to repair muscular dystrophy problems. My major advisor, Erwin Koenigsberg, gave me some advice at that time that I didn't realize was so powerfully influential on the rest of my life. I didn't even understand, I didn't even see it as it came down. And I said, what was that advice? And Irv told me, when I plate the cells out into my culture dish, that if the cells don't look right and they form these irregular looking cells, he said, before you blame the cells for the problem, the most likely source of the problem are the conditions of the environment, the culture medium in which I grow the cells. If the cells aren't growing well, it's not because the cells can't grow well, it's because the conditions I provided weren't the best. After Irv's advice about how the environment changes the fate of the cells, it led to an experiment that changed my entire life, a whole new experiment, an awareness that actually introduced something brand new to the whole field of biology. And that was the understanding of epigenetics. So the necessary experiment to decide how...
This is where it kind of slides off into territory that just doesn't make any sense. Also, he's gonna detail an experiment that he did where he put these myoblasts in different culture conditions and they all became something different. And I could not find this experiment. And like I said in the beginning of the stream, or earlier in the stream, there's a possibility that this experiment was done during his thesis and his thesis just wasn't published online, which is common for people that got their theses work done before the internet was like huge. But yeah, all of the published work from him that I found, I couldn't find this experiment.
The environment was controlling all this stems from a simple understanding. I would put one myoblast in a culture dish and it would divide every 10 or 12 hours. First is 1, then there's 2, 4, 8, 16. And I say after a week, 30,000 cells in the petri dish. Most important fact is all 30,000 cells came from one parent. So I have 30,000 genetically identical cells. What I do now, here's the experiment. I split the cells into 3 petri dishes. So each petri dish has 10,000 cells. But all 3 dishes have genetically identical cells in them. And what do I do next? I said, I changed the composition of the culture medium because the information was saying that the environment in which the cells were growing controlled the fate of the cells. So I make 3 different versions of culture medium. And so each petri dish gets a different version of culture medium with slight chemistry differences. But remember, all dishes have genetically identical cells. What was the result? In environment A, the cells form muscle.
This man seems to think that people didn't previously know that all cells have the same genetic composition. Like, we know. Like, we know. Like, all of the cells in your body have the same genes. It's which ones are being expressed or not. Like, even when he was doing this, that wasn't a novel concept. That wasn't something that he came up with. Like, Waddington had first talked about epigenetics in the 1940s, and he, I believe, got his PhD in the 70s. I could not find anything as far back as 1967 when I did my research on him. So this video says that it's research from 1967. I could not find that. The latest I could find was 1977. And like I said, things might have just not been published. But also, we do similar experiments like this in the lab I'm working in, where we take embryonic stem cells and we differentiate them by using different culture mediums. The issue is, those cells that, like, at the end of that differentiation, let's say we're trying to make, like, muscle, and we're trying to make a lung tissue, or we're trying to make something else. Those different culture conditions don't lead to cells that are directly equivalent to a lung cell that you would find from a human, like just taking a lung sample from my lungs. It's similar. It is more similar to a lung cell than it would be to the stem cell that it started as. But, like, to say that you can perfectly replicate an environment that will turn these cells into specific things is not the case, because it doesn't just take the environment. You have to have signaling between cell types. There are many cell types in the body where they have to communicate back and forth. Like, oh, you're a muscle cell? Okay, I'll be a bone cell then. And, like, that's still signaling. But, like, that's not the environment. That is within you. It's just very strange how he frames things.
In dish 1. But in a different culture medium, environment B, in dish 2, the cells form bone. And in dish 3, again with genetically identical cells, yet a different culture medium, the cells form fat cells. What's the relevance? That was the clear proof that the fate of the cells were controlled by the conditions of the environment, not by the genetics inherent in the nucleus.
Like, yeah, exactly. Like, the problem is it is both. You have to have the genes to make the cells, and it's not going to work on a cell that's not a stem cell. So he started with myoblasts, which are stem cells. And, like, I can't take a skin cell and plop it in this same media and get a bone cell to pop out, because it's already differentiated. And that's the main issue with this. It's not just the environment that controls it. If it was just the environment, then you could just take whatever cell, put it in whatever media, and then make a completely different cell out of it.
Before you blame the cells, as Irv told me, before you blame the cells, consider the conditions of the culture medium. And in the human body, that's blood. Before you blame the cells for pathology, recognize a simple fact that only 1%, or actually less than 1% of illness is connected to genes. Over 90% of illness is connected to how you respond to the environment. And all of a sudden I say, so what's the relevance? Change how you respond to the environment and you change the characteristics of your life. You are the powerful creator, not the victim of your genes.
And that's where you get this weird, if you change your thought patterns, you can change your body. Chicken Bacon Swiss. I am not Hannah. I am Hannah's wife, BAJA. Also, Vortigaunt 841 says hello and subscribes. Thank you so much for the subscription. We're doing a BAJA science stream, and that science stream is actually going to end because I have to go to lab and do my PhD science work. I have to go harvest some embryos. Oh, yes, trespassers will be used for science experiments. I don't know what kind of experiments. Some behavioral studies. We'll stick the person in a room with a shocky button that gives them chocolate. See how many times they press the shocky chocolate button. This is obviously what happens when player 1 chooses the default Hannah costume. What, Hannah? Hannah says, you don't have enough chocolate to sate me. I will take all of the electricity. And yeah, I have to harvest some embryos from a mouse and put them in different amounts of small liquid to prepare them for microscopy. Which is very strange. It's very strange, like, from an outsider perspective looking in, the idea that that's what my job is, to harvest embryos. Mouse embryos, not human embryos. We don't do human embryo research. All right. So that was really fun, everyone. I hope that you enjoyed it. I hope that you got something out of it. I hope that it was, everything that you wanted out of a science stream. I tried to do everything that people suggested. Something that I didn't get to and was probably overly ambitious anyway, was I wanted to talk about a research paper that led to a Nobel Prize from Takahashi and Yamanaka in 2006. I believe that they got the Nobel Prize in 2012. And basically they use mouse embryonic and adult fibroblasts to and turn them back into pluripotent stem cells. And that is so cool. So Nobel Prizes take a really long time. So usually it's like a big gap between when the paper is published and when the person gets the Nobel Prize. So yeah, that was something that I didn't get to because someone had asked about talking about someone that was like a pioneer in the field that I work in, and I thought that they would be close. If anybody has access to like scientific articles, you can search for it. It's Takahashi and Yamanaka 2006, and it's induced pluripotent stem cells. I actually have the paper right here. Yeah. Induction of pluripotent stem cells from mouse embryonic and adult fibroblast cultures by defined factors. It's not a very long paper, and I think that they do quite well at explaining it. So if you're interested, you might give it like a read or a look. It is really interesting, and they take it like a very stepwise process, and so yeah. And if I ever do another science stream, I definitely think I would pick up at this point and talk about this paper, just because it's one of those like mind-blowing papers, and I've read it multiple times, and also it's very close to my research. The lab that I work in, we use induced pluripotent stem cells. We use induced extra embryonic stem cells. And also something that I didn't get to touch on is genetic sequencing, and why it's become so fast over the past decade or two. And I think that's a really interesting topic. So maybe we'll do another one. So thank you everyone for joining me. I hope that you had fun. I'm going to go harvest some embryos, and I think tomorrow Hannah will be back. So thank you all for joining me, and I will see you again soon, I think. Bye.